let's start at the last day of the workshop. The first speaker is Gaston Giribe from Buenos Aires University.
Okay. Let me start by thanking the organizers for the invitation. Actually, I'm happy to be here, whatever it means these days, this kind of sentence. But certainly, I'm happy to see you guys. So I will talk about some particular kind of deformation you can do of ADS3-CFT2 scenario, and specifically, I will talk about some particular UV deformations of that. Let me be precise in later about what I mean by that. But it's related. It's closely related if you are familiarized with the recently studied TT bar deformation. It's not exactly this kind of deformation, but as we'll see, it can be thought of as a kind of single trace version of it. So the reason why I'm interested in that, and this explains part of the title, is that because these deformations are somehow integrable, and integrable in a very precise sense that I will discuss later. So let me start by mentioning two references that appear simultaneously, like 1.5 years ago. That this is 2 years ago. Which is this paper by Serrat, Gideon, Itzhaki, and David Kutasow, and a paper of mine that appeared. I will mainly focus on these two computations, which are computations of correlation functions in this deformed version of ADS-CFT. And also, but this is based on the previous work of them, in which they propose this kind of deformation, and they start to study at least at the level of the spectrum, not yet at the level of interactions, but this is what we did, but at the level of the spectrum. And it's very interesting because also they propose what it would be the deformed dual CFT if you do something very nasty to the bulk, and then I will describe what we do to the bulk. So, but then after that, there's a series of subsequent papers we were working on. This has been in collaboration with Juan Pablo Bavaro, was a former student of mine. Valentino Foy was a student, also a PhD student in New York University, and my friend Matias Leoni, who is my colleague at University of Buenos Aires. And also, this is also, I will briefly mention some, if I have time, something we are doing with Ricardo Stuardo, who is probably connected. He has been participating in the conference. So, but I will mostly focus on this calculation, and then at the end I will discuss these papers. So let me start by mentioning some motivations for studying this. One is the fact that usually it's very difficult to have under control irrelevant deformations in general. I mean, this is a general feature of quantum field theory. It's very difficult to know to handle irrelevant deformation, even to guess what the normalization group flow would tell you in the opposite direction. But then there are some scenarios in which this can be done, or at least it raises the hope of that you can do something with it. And this is these recent models, the people study with this kind of TT bar deformation that Smirnov, Samolochikov, Negro, and Cavalli and other people were studying recently. But then the natural question is how these models in which you can have at least the hope to work out the relevant deformation of in this case of a CFT, how it looks from the bulk point of view. In what sense you can use it to study ADS-CFT. Those that are familiarized with this probably remember the paper by Verlinde and Massey recently, but this is a different kind of ADS-CFT deformation I will talk about. So this I mean, on its own right is an interesting motivation, studying irrelevant deformation of ADS-CFT. But on the other hand, there are other relations that this work has with, for instance, little string theory. Little string theory is a 6-dimensional theory that has no gravity. And this is very interesting. This appears in the near horizon limit of certain fibranes, and this is interesting topic. And also, it can be used. This what I will talk about can be used to say something about the holographic description of this. Also, This is related in many aspects with black holes. I will not have time to talk about black holes, but if you want, we can discuss it later. So let me say which are the relation between what I will talk about and the standard TT bar deformation. I insist with the fact that the one that I will talk about in a very precise sense that I will explain, it can be thought of as a single trace version of it. So, but let me mention which are the analogies with the standard TT bar that Samolochikov and friends were studying. So the first one is that this is a kind of universal deformation, either TT bar and the one I will describe here. Why? Because TT bar is universal in the sense that unless you are talking about the topological theory, you always have a stress tensor. You can have theories, conformal theories, for instance, with different symmetries, supersymmetry, with affine Kac-Moody symmetries, with W symmetries, whatever, but certainly you will have a stress tensor. In that sense, the TT bar deformation is a kind of universal. So studying it is actually studying a huge series of a subset of quantum field theories. On the other hand, the one I will talk about here, since it's a deformation of kind of this sort, but for ADS CFT, we know in the context of string theory, by the way. So in string theory, we have many backgrounds. So these backgrounds here, many backgrounds of string theory. For instance, in the same type 2B, for instance, you have backgrounds of this kind: ADS3 cross S3 cross T4, or S3 cross K3, or even two copies of S3 and S1. Okay, ADS3 cross S3 cross S3 cross S1. So, but always you have this. You will have a SL2 air current coming from the isometries of ADS3. So since the deformation I will talk about involves this current, it will be universal in the sense that all these backgrounds and many others of string theory you can come up with will admit this kind of deformation. And this is as well as a TT bar, but in a different sense, is kind of solvable. In this case, solvable is not like in the standard TT bar in which you refer to integrability, but it's solvable in this, or if you want, it's also integral in the sense that you can compute explicitly correlation functions. You can really compute correlation functions, and this is actually what defines the theory if you have a correlation function. So this, in that sense, is a solvable model. So let me start first by the standard TT bar deformation, because I'm mentioning this, but probably not all of you are familiar with this. Again, this will be a single trace version of it, but let me start with the standard one. So the TT bar deformation, in this case for a conformal field theory, you have an action of a conformal field theory, and then you add a coupling constant, which is of course dimensionful, of this 2,2 operator. So this is an irrelevant operator, so breaks of course conformal invariance. And then you deform, I mean, what it means, this operator? This operator is the stress tensor, or more precisely, this combination of the stress tensor where this theta is actually the trace of the stress tensor. But this is a stress, you can ask what trace, because you are talking about a conformal field theory. But let me point out that this is the stress tensor of the theory already taking into account the deformation, which is not conformal anymore. In other words, if you make perturbations in T, at the first order, you will not have the trace because you are perturbing a CFT, but at the next to leading order, you will have the trace already, okay? So this kind of deformation is very interesting, and it's actually strange, right? It's an irrelevant deformation. If you look at it the first time, you say, oh, I mean, it's hopeless to make sense out of it, or at least to say something about the theory like that, but actually, remarkably, it's not the case. As Smirnov, Samolochikov, Tartaglia, Nero, and his colleagues, their colleagues, they were showed like 3 years ago, is that actually this kind of deformation is a member of a family of deformation that actually preserve integrability in an amazing way. This deformation actually is really, it's like a tangent to the flow that kind of allows you to go in the opposite direction in the normalization group. So this is very interesting model. And what is interesting about that is that it's exactly solvable. So for instance, if you take a circle and time, of course, in 1+1 dimension, and then you can compute explicitly the spectrum of this theory, of this deformed theory for finite T on a circle. Let me show you the energy spectrum. This is the formula. This is a finite T spectrum for a circle of radius r for this kind of deformed theory. Actually, you can explicitly check that if you expand in T, so this 1/T cancel from the first order coming from here, So it actually gives you what you expect, which is indeed the spectrum of a conformal field theory for where H is a conformal dimension, right? So you see, this is the H that gives you the spectrum of the theory you start with, the seed theory, and then you perturb it, you deform it actually. It can be even nonlinearity. So you deform it, and then you get this spectrum, which is exact. So this is amazing to result. And let me say something more about that, which is you can check something about the spectrum of this. So for instance, in this limit in which the energy is actually, so if you want, it's like T is actually small enough, okay? So notice that T has dimension of length to dimension -2. So dimension 2, I'm sorry. And then what you can see is that when T is small enough, you recover the Cardi spectrum, okay? As in the standard CFT, as you expect. But in the opposite, since this is finite in T, if you take T very large, actually you get a Hagedorn spectrum, okay? So you have a model which is an under control irrelevant deformation of a conformal field theory, which leads you for finite T or large T if you want for Hagedorn spectrum, okay? So this is a very interesting thing, and that's why this has been exciting a lot of people. This is a very interesting topic, and what I will describe is a kind of single trace deformation of that. Because the question I wanted to ask is, what about, I mean, my first motivation to study this 3 years ago, was to say, how to make sense out of something similar in string theory. And when I say string theory, I mean at finite alpha prime. I'm not talking about supergravity or next to linear, like alpha prime correction. I'm talking about, let's say, I will focus on perturbations issue strings. So I will talk about a genus, a 3-level string theory or genus 1 string theory if you want also, it's easy to do, but for finite alpha prime, okay? So it will be non-perturbative in alpha prime. So let me start with studying ADS. Why? Because since what I want to do is deform a conformal field theory in the context of string theory, I will start with string theory in ADS3, which has a dual, a two-dimensional conformal field theory as a dual, and then I will see how to deform the theory in such a way that in the dual CFT, you induce a kind of irrelevant deformation. That's the menu today, okay? That's the idea. So let me start very briefly, remembering, I will remind you of the paper of the work of Maldacena and Oguri, which is like 20 years ago, about how to formulate a string theory on ADS3. And this background I will talk about is just with pure Neves-Schwarz backgrounds. The nice thing of this is that you have access to a worksheet formulation, and then you can solve the theory, the spectrum exactly, and correlation functions. You can compute correlation functions, integrate them, and have string scattering amplitudes. That's the reason why this model is very good, again, because you have access to the worksheet formulation. So, and there are two kind of, I will briefly summarize what we know about this model. So in the string theory in ADS3, this is supported by a B-minimum field. So you have a B field that pushes the string to the boundary. So there is a competition between gravity and the B field. And this is the reason why you have two kind of states in string theory, the so-called short strings and the so-called long strings. And those are the ones that I'm just putting here. So these that are confined in the middle are short strings in ADS3 and have discrete spectrum of energy. And those that come from infinity and bounce to infinity, these are long strings, and they have this continuous spectrum of energy. So string theory has SL2 cross SL2 isometry, of course. Then you can see that if you formulate string theory on this background, on ADS3 with B fields, the model turns out to be a Bessumino-Witten model. So the action, the Polyakov action on this background, you formulate it, and as soon as you put ADS3 in its Lorentzian form, you get that the action becomes a SL2R Bessumino-Witten model. So it's a conformal field theory, it's a non-compact conformal field theory, can be complicated to work technically, but formally it's very well defined, and then you can at least hope to quantize the spectrum exactly, and actually you manage to do it. And the main reason why you manage to do that is because it's a conformal field theory, and you know that it's an exact point, so it's exact conformal field theory to all orders in alpha prime, so solving the beta equation to all orders in alpha prime, but also since it has SL2 symmetry, it actually has more symmetries. It's a Kac-Moody symmetric CFT, has an affine symmetry. This is to say that you have this infinite dimensional algebra, which have a current. These are given by that. The modes, the Fourier modes of this current generate this algebra and the standard nomenclature, right, of the affine Kac-Moody symmetry. So you have these 6 current representing the 6 symmetries of this. Okay, 6 local current that expand the affine Kac-Moody symmetry, which roughly speaking, as we know, is the square root of Virasoro. So this is the conformal theory. In particular, the commutators of SL2, of the central extended SL2, because it's a Kac-Moody algebra, is actually encoded in the OPE of this current, in the operator product expansion of this current. So where ellipses stand for subleading terms. So this, for instance, reflects the fact that the commutator between the shade tree has a central extension. And this K is the size, K is the analogous, the 3-dimensional analogous of the square root of a 2th coupling, if you want, because strictly speaking, is the radius square of ADS divided by alpha prime. Okay, so the large K limit corresponds to a semi-classical limit. Okay, here I will talk about finite K because I don't care, because I can do it basically. So then you have these vertex operators. Since you have access to a worksheet formulation, you can ask yourself, okay, I have a CFT. I know I have an action for it. This CFT, I'm lucky enough to say on top of that, it has this Kac-Moody current, so it has a lot of symmetries. I know how to represent this Hilbert space because it had to fit in certain subset of representation of SL2R because it's the symmetry of the model. And then I just ask myself which are the primary operators of this theory, and then I have the vertex operators that describe my string spectrum. And these vertex operators, these vertices are the one that I call a phi. Okay. This phi, which have some labels that actually correspond to the momenta in the ADS3 space, okay? So you can think of it algebraically as labels of SL2R representations, but of course they have a physical meaning, and the physical meaning is the one that I just explained here. The energy is given by m plus m bar plus this number. Notice I will describe all these numbers in a second, and the angular momentum, so the string has a certain angular momentum, and it's given by this. So this part can be thought of as the kinetic energy of the string. Okay, so this is time direction. So this is the kinetic energy of the string, but then there is this piece here where omega is actually the winding number of the strings. Because remember that there is a B field pushing the string to the boundary. So the string has a winding number, which is not topological, but it's there. And then it's reasonable physically that this appears in the energy in this way, because as I mentioned before, K is like R squared over alpha prime. So this is proportional to the tension of the string. So what it means is that they have the tension times the winding number. We'll say how many times it runs around itself. So this is the spectrum of string theory in ADS3. Okay, and then you have the worksheet theory with certain symmetries given by this, which are the analogs of the momentum in the worksheet momentum dx in standard string theory. Then you have the vertex operators, and then you have the vacuum, the excitation vacuum. You apply the vertex operator, you go t going to t set going to 0 or infinity, and then you get the either ingoing or outgoing states and so on. Okay, so these are the labels that represent the strings in the worksheet. If you are a very mathematical person, you can think of them as the labels of SL2R representation. And then you can study the representation. This is what Maldacena and Oguri did. This is a kind of pretty technical. I will not enter into details, but this is summarized here. What it means is that you will take into account continuous and discrete states of SL2 representations, but physically what it means is you will take into account strings with continuous spectrum, which are non-localized, like these long strings, and then short strings with discrete energy spectrum. So this they correspond to a continuous and discrete representations of SL2R respectively. So everything is very natural. Okay. So any questions so far? Okay, that doesn't work like this now. Okay, doesn't matter. So I hope this is just a summary of Maldacena and Oguri series of papers between 2000 and 2001. Okay, what I will do now is say, okay, if I have a string theory in ADS3, I certainly have a two-dimensional dual CFT, which is the one that lives here in this boundary. Okay, so this boundary I will parameterize with certain variable, let's say x and t, or whatever. This is the boundary, and this is the bulk direction. So we have these vertex operators describing the strings. Okay, the worksheet of strings have seed coordinates. That's the reason why I have this seed here. And in the boundary, I have these operators with certain conformal dimension h that live in the boundary in the dual CFT. What it can be tricky here is actually that we are talking about two different two-dimensional conformal field theories: the worksheet conformal field theory and the dual conformal field theory. In this case, both of them are two-dimensional. So let me focus on that, just to pay attention for not, if you don't confuse the coordinates, everything is okay. So x and x bar are the coordinates in the boundary, and seed bar are the coordinates in the worksheet, as usual. Okay, I will integrate the worksheet at some point. So, but x and x bar will keep there because it will be local operators in the boundary. So you can ask how x and x bar appear here. I mean, because I don't see them anywhere. Where is this operator located? X and x bar appear as if you want, is the conjugated moment, is the conjugated coordinate of the momentum given by m and m bar. Okay. Okay. It will be like I will be in a second clear. So from the worksheet point of view, this x and x bar will be labels, will be auxiliary variables. But from the dual point of view, will be the point where the operator is located. Again, from the bulk point of view, this will be auxiliary variables that helps me to parameterize the spectrum. And in the dual CFT, this will be the location of the operators. To be more precise, pay attention to this expression. I will take the currents, J3, J plus, J minus, and also I have an analogous expression for the bar components. And then X appears here only as an auxiliary variable that permits me to encode in a single local operator, now depending on the two kinds of variables, the currents of the worksheet CFT. So from this point of view, X is an auxiliary variable that just allows me to organize the things. But also, again, it's related to by a Fourier transform with this coordinate with the energy and the angular momentum, okay? So then you can ask, okay, I have a dual CFT. Let me start from the basic of a CFT, which is a stress tensor. It's the thing that for sure I know it is there. And this has been worked out in 1999 by Seiberg and Kutashov. And you can see explicitly that T and T bar in the boundary CFT, notice that depends on X, and I don't see, this is not a worksheet one, it's a boundary CFT. It can be written as a certain combination of some operators and currents in the boundary, where this guy is this, integrated on the worksheet. So this particular form they come out with, well, you can show that this has the right dimension, and if you compute the OPE, gives you this OPE, which is this is the standard 6k/2, as you expected from the 6k is a dual conformal field theory, as computed even before by Gideon, Kutashov, and Seiberg. So it looks like a stress tensor. It has the same dimension. It has the right OPE. It has, I mean, this is a stress tensor of the dual CFT. So now we have ADIS3 under control because you have access to a conformal field theory, a worksheet conformal field theory that describes string theory and ADIS3. And in the dual model, you have a stress tensor you can write down explicitly, integrating the worksheet variables. So we are in a situation of saying, okay, now let's do a TT bar deformation of the dual CFT and see what happens inside. This is not what we are going to do. We are going to do something a little bit more sophisticated. So what we do is the following. We have this operator, the stress tensor, the T seed component, and the T seed bar component of the dual CFT, this one, not the worksheet CFT, the dual CFT. And then naively you say, okay, you can make a TT bar deformation. What Gideon, Itzhaki, and Kutashov realize is that there is another kind of interesting deformation you can do that is actually marginal from the point of view of the worksheet. It doesn't mean that in the dual CFT, it will induce a marginal deformation. Actually, it will induce an irrelevant deformation. But from the worksheet point of view, it's marginal. This will be interesting, okay? So, but which is this deformation? It's a kind of single trace version of TT bar. This I anticipated. And then I mentioned that
you have 5 minutes left.
Really? Okay.
Yes.
Okay, so the thing we will compute is actually this one. This operator is like, instead of multiplying t and t bar, I just put the integrals together and integrate it only one time in the worksheet, not one time and the other one. This is a marginal deformation from the worksheet point of view. And then it can be, you can show that this corresponds to just having two currents in the worksheet point of view. This is marginal from the worksheet point of view, but induces an irrelevant deformation in the boundary. So let me just say what we did is just take this worksheet action that describes sigma model and ADS3, put this current deformation and compute correlation functions. That's what we did. Okay. So let me show you. It doesn't matter how we compute it, but basically we parameterize ADS3 in a precise way. The only subtlety here is that this correlation function have these logarithmic divergences. And then we have to regularize something. These logarithmic divergences come actually from the insertion of this operator, okay? So what we did is take string theory first, just with certain special coordinates, which are depicted there. This is the action. If you evaluate it with some, you have to add some auxiliary fields. Basically, this is the undeformed model, and then you put the JJ bar deformation. If you put that, you get this action. This again is a marginal from the point of view of the worksheet. So describe string theory in a different background. Okay, it's not ADS3 any longer, and it's actually a background that very close to the center looks like ADS3, but as soon as you want to go to the boundary is no longer there. And then you find a linear dilaton flat direction, which is a background that typically appears in little string theory. So you have interpolating background, which is ADS3 inside and then becomes flat space with a linear dilaton. And this is an exact background of string theory to all orders of alpha prime because you are solving this at finite alpha prime. This is an exact conformal theory. This is the background we have. And this is what they know, what they show. This is the metric. If you want to play with it, you can see this is a highly non-trivial metric. It has negative, positive, and zero curvature, depends on the part of the space. It's conformally flat anyway, so it's dual to PP waves. So it's very interesting background by some right, and this is what we are studying with Ricardo. But let me just say that we computed correlation function. Let me tell you the results we get. And so this is just technicality, how we do it. We have to integrate in the worksheet because we don't want to do it perturbatively. And basically, we just integrate, we use some theorems, and then we can solve it explicitly, at least at the level of a two-point function. The only problem we have is that we have to regularize something. There is some, when we do it with the path integral, there is some Liouville factor that factorizes out, and then there is a logarithmically divergent ultraviolet integral that we have to regularize. You have to regularize it, and you can regularize it using different methods. All of them agree. And basically what we get, let me say the result, this is similar, this was an analogy because the regularization we do, the kind of integrals you do is similar to what happened, for instance, in the T-ring model. And then, so just getting inspiration from that, we were able to compute, this is what it shows, compute the two-point function, okay? This is explicit form of a two-point function. These funny gamma functions come from a Liouville factor that factorizes out. But then, remarkably, we got the exact correction of the, so if you don't put this guy, remember the lambda was the coupling constant of the deformation. This is not perturbative. I mean, we didn't make a first order in alpha prime. This is actually the full deformation of the spectrum. So if you compute the spectrum of string theory, H0 is the spectrum of the undeformed theory, and H is the spectrum of the deformed theory. So you can see that if you put lambda to 0, actually H becomes H0, and this is the full spectrum of the theory. So then what it means is that now we have, for this deformed theory of a background of string theory, two-point function of a string theory that lives in an interpolating background, that inside is ADS3 and then becomes a linear dilaton flat space-time, and we have the two-point function. Then you can think of it and, okay, we have the two-point function. Let's try to think of it as a two-point function of a dual theory. What it means, this dual theory? I know that if I don't deform the theory, I have a string theory in ADS3, and the dual theory is a two-dimensional conformal field theory. Now I'm deforming the background. What I get in the dual theory, if something. So this is what we study in our papers, and also Kutasov, Itzhaki, and Gideon. And then you can see that this dual CFT is actually non-local. You can see that because you can study the Cutler-Lehman decomposition of the form we get, and this is related to this factor that appears here. And there are a lot of subtleties. But the important thing is that it's a non-local CFT, or more precise, non-local quantum field theory, because it's an irrelevant deformation in the dual theory, marginal in the bulk, in the worksheet, but irrelevant in the dual. And it's a non-local theory. And this is something you expect from previous results about what it could be the dual to a little string theory background. And this is what we get very far, a linear dilaton background reminiscent of little string theory backgrounds. So this is our result, is the result for the two-point function and for the spectrum of operators. And it's actually very reminiscent of what happened, if you remember, with the spectrum of the deformed CFT, with the TT-bar formation. Okay? So what we did also with Matthias Leoni also was, since there are some regularization and renormalization involved here, what we did is computing other observables just to check that indeed our regularization schemes were consistent and everything works. We did it for the sphere, endpoint functions also, and on the disk geometry, and everything is consistent. So of course the expressions are more involved in that case because you have boundaries on the disk and so on and so forth, but basically we check all these observables and more recently the endpoint function of the sphere also, and everything works well. So let me start here.
Okay.
Up here.
Thank you very much. Okay, questions? Carlos Nunes, please. Carlos?
Yeah, I'm here.
Ah, okay.
I see that question. Can I ask it? So, Gaston, okay, I have a couple of questions. So the first one is, here you are seeing a Hagedorn spectrum, yes? So
yes.
If we go by what Alejandra explained on Monday, this would suggest that the thing does not have a supergravity realization. Is this what you see? Because on the other hand, if you suggest a little string theory, it does have a supergravity realization, not of course as an ADS, as a 2D thing, right?
Well, I think the dual CFT, I mean, you can do this for the superstrings on ADS3. Actually, I did it. If you look at my formulas, you will see that there are a shift in K that actually corresponds to a superstring theory, because I didn't put the fermions because the fermions just are simple. But so this works for, namely, you take, for instance, supersymmetric background, NS1, NS5 system, you take a look at it, get this background of type 2B, and then there is an exact ADS3 cross S3 cross S3 cross S1, or ADS3 cross S3 cross K3. And then you get these backgrounds, and then you do superstrings there. And then you can do that. And the dual theory, whatever it is not a standard quantum theory. It's a non-local theory. But I don't think that you cannot have supersymmetry in that case.
No. Okay.
I think
but then maybe the second follow-up question is, why, if you didn't insist on any ADS3 of, why you get into, so there are two little string theories, the one in the Neves-Schwarz in type 2A and the Neves-Schwarz in type 2B.
Yes,
right?
The type 2B.
Why?
Well, I mean,
because I give you an idea.
Yeah, you can. No, that's a good question. This appears because, first of all, you can make a brain construction of it, and it involves some 5 brains and 1 brains, and then you can see what happened with the background when you find this deformed background. This background, even in supergravity, you can find it, and it's a solution of type 2B supergravity with certain fluxes from the NS5 brain, which is related to this K. And then you can see that this particular background on which I'm formulating string theory appears as a background of the, it's a background that appears in the type 2B that very far becomes a linear dilaton.
But if I give you an ADS3 in type 2A, right? I give you some ADS3 in type 2A, right? And I do the same thing that you have done that was completely ADS3 based, right?
Yeah.
Why will I fall into the type 2B? Little
well,
string.
I need remember that these are Neves-Schwarz backgrounds, right? Pure Neves-Schwarz.
Okay.
That's the answer, I think.
Correct.
Of course, you can make some duality and so on, but
Okay. That answers. Thank you.
Okay. Question by Carlos Cardona. No?
again.
Carlos?
Trying to unmute myself. Now I'm gonna start my video. There we go. Hi Gaston. Nice talk. Yeah, I'm pretty ignorant in this DT deformation, so I just found it very interesting. Thank you for your talk. So yeah, I have a couple of questions. So you are starting with the usual, string theory ADS3, which is supposed to be dual to these orbifold constructions, CFTs. So if you think about the deformation as just a small deformation of the ADS3, right? You are not going too far from the original ADS3. So I guess your lambda parameter is small, I guess. So can you still relate this to the orbifold, to some deformation of the orbifold CFT construction, for example?
Yeah, yes, it's a very good question too. So let me say the following. The dual CFT of this deformed model is actually known. It has been proposed by Gideon and these people, no? And actually what corresponds is, as you mentioned, the dual CFT. In the standard ADS3, you get the dual model is this orbifold point, right? It's an orbifold. You take n copies of your CFT, you divide, you mod out by a symmetric product, by the permutation group, and so on and so forth. But then this model, also the dual theory, is supposed to be the conjecture they have, and they have several checks, that a copy of is a symmetric product of a TT-bar deformed CFT, okay, in a dual point of view. So in that sense, just the first thing. The second thing is that, of course, you can make approximation in lambda, okay, small lambda, but it doesn't mean that your theory departs a little from ADS3. What it means is that the size in which the space will become a flat linear dilaton background is farther, but eventually you will reach it. You see, because lambda, the coupling here, what it tells you is where your CFT will start to not having a boundary of ADS3 and becoming flat space. So that's why the reason why we prefer to do it non-perturbatively and just compute the correlation function. Not only because we could, because also because this is what it's sensible to do. Because small lambda just tells you, you will have problem, man, but in the future eventually.
I do have a couple of questions, but I'm going to save it for the discussion. But now that you touch on that interesting note, let me just ask. So if lambda goes to this regime when you are starting to see now a flat background. So and you say we know the dual description of these strings in that background. So is this a kind of flat space
yes.
CFT holography?
Yes, actually, if you see I'm very bad to putting titles in the papers. So my paper using correlation function was very ugly title. But their paper, the one that's simultaneous because we arranged to put the paper the same day, is called Holography Beyond ADS. And that's the reason. That's the reason. Because this is a flat holography, a kind of, because you have a linear dilaton anyway, but it's a kind of flat holography. But this is probably not surprised. There are some papers in the 99 of Cyber and people trying to make this dual of a little string theory. So, but yes, the answer is yes.
All right, thank you.
Okay, we have just 1 minute, so Eloy, you can ask your question, please.
Okay, I have a naive question, Gaston. If I understand you well, the calculation in the ball are possible because ADS3 is an exact solution in the sense that it exactly banishes the conformal anomaly. In what sense do you think that it is possible to extend this calculation for other exact solutions, like those that we studied some years ago, which are fixed points of...
It's not some years ago any longer. It's more it's like 15 years ago. But yes.
And the second part of the question is, do you think that the fact that they will be fixed point of the duality will will imply some roles or will be important or not?
Well, yeah, that's a very good question. So let me say the following. Even my deformed background, it's not mine. I mean, it's actually the deformed, several people study this background at the same time. So this deformed background is an exact solution of string theory. Even with lambda, it's an exact solution. You can prove it because, as you mentioned, the first one is IDS3, and then you get this additional one that is an exact marginal deformation. And then it's the exact background. This background is there too. But your question is about other backgrounds, like a certain no background, like a certain like BTC background. And actually, you can do it for BTC, for instance, because it's an orbifold. I mean, all of them are orbifolds of this guy.
Yeah, but BTC is not the fixed point of the duality, no?
It's not a fixed point of the duality, but this is still an exact solution. And the people study that, actually. I mean, there are some papers of Kutasov and these people recently studying this kind of deformation, but for the BTC, for instance. And what you get in the dual theory, how you do it. Yes, you can do it, and the people have done this. They didn't do it for other backgrounds like Cossert-Hainaut, which are a little bit,
So this is a way to obtain new holographies, new realizations.
Yes. Well, I mean, by its own right, even if you are not into this kind of deformed holography, you don't trust them, there still are new exact backgrounds of string theory, right? In which you can compute correlation function. This is interesting by its own right because it's at all alpha prime.
Thanks, Con.
Okay, so I'm afraid we have no more time left. So I'm afraid, Jeremias, we have it ask his question in the discussion section. So we have now a 5 minutes break. Okay.
Okay, thank you very much.
Thanks, Gaston. Hi, Diego, can you hear me?
Yes, I can hear you very well.
Okay.
So at the moment I'm sharing the screen, right?
Sorry?
At the moment I am sharing my screen. Is that right?
Yes, it's okay, your screen. Yep.
Okay.
Okay,
No, the thing is,
so,
I don't see, and I don't know if there is a way of seeing, I don't know, the other cameras or other captures, right? But anyway, it's okay.
oh, it's fine.
Perfect.
We can see your slide and we can hear you.
Okay, okay, and now it's not in the full screen mode yet.
Yes.
Okay.
So the next speaker is Diego Correa from Universidad Nacional de La Plata, who is going to talk about Wilson Line's ADS-CFT CFT1 realizations and mixed boundary conditions.
Okay, well, thank you, Victor, very much. And well, I should start thanking the organizers. Yes, but also thank to the many others collaborating and supporting this idea of the LAWGH network. Okay, well, today I'm going to be talking about some work done in collaboration with Victor Giraldo Rivera and Guillermo Silva, and it's about mixed boundary conditions in ADS2 and how is this interpreted in terms of Wilson lines. Right, let me just, so this is the plan of my talk. I will precisely motivate this idea of Wilson lines as one-dimensional defects. I will discuss a bit what kind of operators or insertion we would like to consider in the line and how are they related to fluctuations in the dual string description. And then I will just focus on the particular kind, on certain kind of mixed boundary condition for these fluctuations on the worldsheet, and okay, apply these ideas to the case of Wilson lines in ABJM theory. So, well, it should motivate this. Well, as you know, while CFTs are central in the understanding of the realm of quantum field theories, and okay, and CFTs are typically defined in terms of conformal data, and the conformal data is not just correlators of local operators. You also need to include in your descriptions defects of many dimensions, or many codimensions, and Wilson loops are just a particular kind of one-dimensional defects you could consider in any conformal field theory. So of course I could say many other things about Wilson loops. They are interesting per se. They have very nice physical interpretations, although I know we're not talking about them today. Also, Wilson loops are a very nice arena to play with many sophisticated theoretical tools that has been developed in recent years. At least this is also a motivation for me to study them. So let us start. Well, I should at least provide to you a very basic notion of what a Wilson loop is. Okay, a Wilson loop is a non-local observable that measures some non-abelian phase that a particle, an external particle, acquires when it is forced to follow some contour. And then it typically depends on two things. Depends on the contour where you move around this external particle, and also what kind of particle do you move around. And this is encoded in the representation in which you take these trace. So this is the most basic ordinary Wilson loop you can define in any gauge theory. But today I also will discuss for you some other fancier Wilson loop, which is this so-called Maldacena Wilson loop. For instance, you could define in n equal 4 super-Yang Mills. So in n equal 4, in addition to the gauge potential, you have many other, well, you have all the fields in the adjoint representation, but in particular, you have 6 scalar fields. So you can define this Wilson loop that couples not only to the gauge field, but also to the scalars through this coupling specified by this 6-dimensional vector, n, which can in general be a function of the parameter of the curve. But the thing is that if you take this unit vector to be, if you take this vector to be unitary, this Wilson loop is locally supersymmetric, and as you might guess, this is typically quite convenient. So since I would like to discuss this problem in the context of the ADS-CFT, correspondence, I should tell you what it is, the description of a Wilson loop in the dual gravity side. So at least for the fundamental representation, which is the case I'm going to be considering today, you can compute expectation value of the Wilson loop by computing the partition function of an open string. And the information about which contour you are considering is centering as a boundary condition. More precisely, you have to compute this path integral over all the configurations of open strings that their endpoints land on the contour at the boundary of ADS. So, okay, this is typically, so this is a sketch of one of those configurations. This is typically a very complicated computation to do. But if you're in a regime in which the coefficient that is in front of the string action is when this coefficient is very large, this is typically the square root of the Toff coupling in the dual gauge theory. When this is very large, you can just approximate this by a saddle point. And at the end of the day, what you have to look is you have to, among all the possible open string configuration, you just focus on the one that has minimal area. So just to set an example, and because it's moreover the example I'm gonna be interested today, let us consider the dual of a straight Wilson line. So say we consider ADS t+1 in Poincare coordinates. So this set variable is just the radius of ADS. And okay, and the boundary is at z equal to 0. So here at z equal to 0, we have a straight line. So it turns out that the minimal area configuration with this boundary condition is a worksheet that extends all the way on z and some transverse coordinate t. And then if you consider the pullback of this worksheet, the induced metric on this worksheet is again an anti-de Sitter, is an ADS2. So, and then the appearance of an ADS2 should ring a bell. Precisely what this is indicating as that in the dual description, in the dual field theory, there should be an object one-dimensional with conformal symmetry. So this is where are we going? So we would like to consider Wilson lines as conformal defects. So say we have a d-dimensional, a field theory of d-dimensions, so a conformal dimension, sorry, a conformal field theory in the dimensions. So we have this SO2, T conformal group. And of course, if you consider a line, a defect, a one-dimensional defect, you're gonna break this conformal symmetry, but you cannot break it completely. There is the hope of preserve some of the result of the conformal symmetry. And the best you could do is just to preserve what would it be the conformal symmetry on a line, which is an SO2, and the rotations that could be in the directions transverse to this line, which is in this case could be an SOT-1. So an example of such a one-dimensional conformal line is the half EPS Wilson line in N=4. This Maldacena Wilson loop, when you take, in this case, you just take the coupling with the scalars to be constant and in a very specific direction. So this is the symmetry you have. We have the conformal symmetry in one dimension. This is the transverse rotations. We have this additional SO5, which is what remains of the R symmetry. Once you fix phi 6, you can still rotate the other scalar fields, and this is a symmetry of this Wilson loop. And on top of that, you have 16 supersymmetries, and all together, you have this OSP 4/4 symmetry group for this line. Excitations of this Wilson line are going to be accommodated in representations of this group. So, but okay, since we would like to consider excitations and correlators of excitations in this line, we need a notion of what a correlation between excitations is for these Wilson lines, and that's very simple. We can compute, we can get the notion of correlation functions by exciting the Wilson loop by inserting n=4 super Young mills along the line and compute the expectation value of this. So this is our definition of correlation functions in the line. And of course, if the theory is conformal as usual, this is restricted by the symmetry in the usual way. So the 2 points is correlation function is just encoding the spectrum of scale dimensions. The 3 points correlations are just giving the structure, sorry, the structure constants, and you could go and compute higher point correlation functions using an operator product expansion. So what I should discuss now is what kind of insertions. We can consider any kind of n equal 4 operators inserted in the line, but what are the ones that we'll be interested in? And okay, whenever you have a defect, a very important multiplet to consider it is the so-called displacement multiplet, which in this case is the following. In the case of the supersymmetric line n equal 4, is a set of 8 bosonic and 8 fermionic insertions you could consider, and are the following ones you can consider. Recall that we have in mind this Wilson loop, this Maldassena Wilson loop, in which we have taken the phi 6 as the internal space direction. So we can have insertions made out of the remaining 5 scalar fields, so that they are 5 and they have scale dimension 1, and we can have also some other kind of transverse excitations, which are these displacement components. We have 3 of them, and they are combinations of the field strengths and the covariant derivative of the phi 6, and they have scale dimension 2. Of course, we can have fermionic insertions, and we have 8 in this multiplet, and they have scale dimension 3/2. Well, the nice thing about this is that they are very nicely interpreted in the dual description. If you compute fluctuations around this ADS2 worldsheet in the static gauge, of course, for instance, focus on the coordinate excitations in the target space fluctuations, we are going to have 8 transfer fluctuations. Recall, this is an ADS2 in ADS5 times S5, so we have fluctuations in the phi sphere. All of them are massless scalars. And then if you look at the usual relation between masses and dimensions in the ADS-CFT dictionary, massless scalar fields in ADS2 are precisely in correspondence to operators with dimensions delta equal to 1. And moreover, we can also have excitations in the ADS part of the space, transverse to the ADS2. In this case, the excitations are massive. They are 3, and they have a mass square equal to 2. And again, they are in correspondence with operator of dimensions delta equal to 2. And also, you have 8 fermionic fluctuations, and their masses also matches the dimensions of the fermionic insertions in the displacement multiplet. Good. So why do we call them displacement operator multiplet? Well, because they are components, this is what they do. If you consider, say this sketch here, a Wilson line with a small bump and a small deformation in a transverse direction to the line, the variation of the Wilson loop operator is precisely represented by an insertion of a component of the displacement multiplet along the Wilson line. So, okay, this is, as I said, very standard and very basic thing to consider when you have a defect. But today, my point, the point I want to make is that it is also interesting to consider other kind of deformations, those that you can build out of the phi 6 scalar field you use in the definition of the Maldassena Wilson line. Why? Because we using this kind of insertions, you can build this other Wilson loop, which is also very interesting. You see, now we have put a set a parameter in front of the scalar field. So we can interpolate with, say, we set zeta equal to 0, and this is the ordinary Wilson loop. And if we set z equal to 1, this is the Maldassena Wilson loop. For any other value, this is something in between, interpolating between the ordinary and the Maldassena Wilson loop. And now, why is this related with the phi 6 insertion? Because if we now expand these operators, say near z equal to 1, we have to lead in order. This is the Maldassena Wilson loop, and the following orders are just insertions of phi 6 integrated all over the line in the Maldassena Wilson line. So insertions of phi 6 is the way to build out this interesting interpolating Wilson loop between the ordinary and the Maldassena Wilson loop. The thing is that when you try to compute the expectation value of this Wilson loop, then you realize that this zeta coefficient you introduce needs to be renormalized, and moreover it runs, and you can compute a beta function to it, and this is been done by Polchinski-Sully, and in more detail more recently by Beccaria, Chomby, and Zeitlin, and this is what you get. So essentially, what we are having here is like this parameter we have introduced is a coupling constant in this one-dimensional defect theory. And okay, there is a renormalization group flow in this theory. And then by inspecting this beta function, we see that there are a few fixed points we can consider. For instance, the zeta equal to 0, the value zeta equal to 0 is the UV fixed point that it corresponds to the ordinary the ordinary Wilson loop. But then there, at that point, if you consider this insertion by this phi 6, you see that this phi 6, as I mentioned, that's a little bit below 1, so it's an irrelevant deformation of this conformal point. So it triggers a renormalization group flow that takes you all the way to this other fixed point, which is zeta equal to plus or minus 1, which is an infrared fixed point where do you have the supersymmetric Maldacena-Wilson line. So, and this is interesting. Why? Sorry, because this Wilson loop is interpolating between something whose dual description was proposed to be in terms of Neumann boundary conditions for all the coordinates in the phi sphere, all the way to some other operator whose dual description is in terms of an open strings who's satisfying Dirichlet boundary conditions for the coordinates of the phi sphere. And that's nice because since many years ago, we knew, thanks to Witten, that we could use mixed boundary conditions. This is what you expect to have an interpolation between Dirichlet and Neumann, can be associated with renormalization group flows triggered by multitrace deformations. So this is exactly what Polchinski and Sully did. They took this idea. So this is, what I'm writing here is just if you want the phi massless scalars associated to fluctuations in the phi sphere, you have phi of them. So this is the typical behavior, but now in the specific case of having d equal to 1 and the mass equal to 0, so you have the delta minus behavior is 0. The two possible behaviors, fall-offs of the scalar fields are just constant or with the power of z which is equal to 1, delta mass is equal to 1 in this case. So by using like a quadratic the boundary term, they could derive this linear mixed boundary condition that you see interpolate sets. You put chi equal to 0. This is the boundary condition will be beta equal to 0. With beta is just the normal derivative of the scalar field vanishing, or when chi is very large, they could be like setting alpha equal to 0, which is like the Dirichlet boundary condition. So it interpolates between Dirichlet and Neumann, and this parameter chi is dimensionful, so that's why it breaks conformal invariance. This also breaks supersymmetry in the case when all the fermions have mass 1. Okay, so well, in what it remains of the talk, I'm gonna just discuss these ideas in the context of Wilson lines in AVJM. So AVJM is a three-dimensional theory where you have two Chern-Simons groups, if you want, UN and UM, and different hypermultiplets matter in the fundamental and the fundamental of these groups. Of course, there is a half EPS Wilson line in this theory. This is the aspect is a little bit more intricate than the case of the Maldacena-Wilson line, but you see you have the gauge fields, and also you have the matter fields entering here. You have this product of scalar fields, but you also have the fermions in these orthogonal blocks of this kind of the superconnection. This N matrix entering here is somehow specifying the orientation in internal space. But for some reason, in AVJM, there is a richer family of Wilson lines, of supersymmetric Wilson lines you can consider. And one example of this is, for instance, this generalization of the superconnection. You see, is a little bit different because I am now introducing this zeta coefficient in front of the coupling with the fermions, and the same coefficient is entering in this matrix M that specifies the orientation in internal space. So the thing is that this is supersymmetric for any value of zeta and it preserves for supersymmetry, which is 1/6 in the context of APJM, and it interpolates between when you set z equal to 1. This is a half DPS Wilson line of the previous slides, and in that case, the dual description is a string located at the very specific point of the compact factor of the dual geometry, which is CP3. So it has a Dirichlet boundary condition for all the angles in the CP3. And when you go all the other way to z equal to 0, this is you don't have the fermions anymore. Here you have the matrix is -1, -1, 1, 1, and this is the usual bosonic half DPS Wilson loop that was conjectured to correspond to an open string in which two of the coordinates of the CP3 has been smeared. So you could be imposing Dirichlet boundary conditions in 4 of the 6 angles and Neumann in the remaining 2. The other thing which is very important to us is, okay, you could expect at this point that you might have something similar to Polchinski-Sully because you have some Wilson loop that is interpolating between Dirichlet and Neumann boundary conditions for 2 of the angles in the CP3, but it's not exactly the case. And okay, revealing what is the dual description of this was kind of the main motivation of our work. A central point in looking for this dual description of the appropriate boundary condition to describe this interpolation is that, in contrary what happened for the case of Polchinski-Sully, if now you compute expectation value of this Wilson loop with this zeta parameter, you see that the BEP is independent of this coefficient that distorts and interpolates between the two cases. So now if you think that, sorry, that the expectation of the Wilson loop specifies the free energy of the one-dimensional theory, this is like this interpolation rather than an Archie flow. It should correspond to the marginal deformation of the theory. So, okay, so this is, well, in order to reveal or to define or to look for this dual description of these guys, we need I need to tell you what it is the dual description of the Wilson loops in these AVGM theories. So as I said, now ADS2 is a worldsheet that is expanding in ADS 4 times CP3. The mass spectrum is slightly bit different than now. We have, so for the fluctuations in the CP3, we have 6 massless scalar fields. We have only 2 transverse fluctuations in ADOs. They have mass square 2 as well. But the main difference with respect to the previous case is that now out of the 8 fermionic fluctuations, we have 6 of them having mass plus or minus 1, but we have 2 massless, fermions, and this is crucial in our analysis to have supersymmetric boundary conditions other than Dirichlet. So let us discuss with a bit of detail supersymmetric boundary conditions in ADS2, trying to look for supersymmetric mixed boundary conditions. So Neumann and Dirichlet have been analyzed in the 80s. So we would like to consider the case of a complex massless scalar field and a massless spinor in ADS2. Those are the supersymmetry transformations. If you work in Poincare coordinates, this is very simple to get an explicit expression for the Killing spinors in ADS2. So they parameterize 4 real supercharges. Then we expand the solutions to the Klein-Gordon and Dirac equations for the scalar and the fermion. And we have these expansions, and then replacing this expansion, these Killing spinors in these supersymmetry transformations, we obtain like the supersymmetry transformations of these functions alpha and beta, or entering the expansion of the scalar field, or this eta minus or eta plus entering the expansion of the fermionic fields. And you see that now if we want to set Dirichlet boundary condition, that would be saying alpha is equal to 0, this is preserved if you simultaneously impose that eta minus is 0, or you can demand that beta is equal to 0 as a boundary condition that would correspond to Neumann if you simultaneously demand that eta plus is equal to 0. So we have now the possibility of having Dirichlet or Neumann boundary conditions for the scalar field with some consistent condition in the fermions, and preserving 4 supersymmetries. So the question is whether we can do it.
Diego, you have
we can,
5 minutes.
okay. The question is whether we can have mixed boundary conditions, and the answer is yes. We can consider, for instance, this kind of mixed boundary conditions, chi alpha plus beta equal to 0, and this is supersymmetric if you require this other mixed boundary condition for the fermions. But the thing is that you have to restrict the Killing spinors to be constant, and so this kills 2 of the possible, the 4 supersymmetries we had in the previous cases. And moreover, this is not a good candidate either, because this coefficient in this combination is dimension full, so you expect this to break conformal invariant. So we have supersymmetric and conformal mixed boundary conditions. Recall that alpha and beta has different dimensions, so the answer is yes. So we would like to have a mixed boundary condition that combines alpha and beta with a dimensionless parameter, interpolating parameter, and the way we did that was to combine beta with the derivative of alpha. If you do that, beta and the derivative of alpha have the same dimensions, and this is a dimensionless parameter. Again, we can see that this proposal is supersymmetric if you impose these other conditions on the fermions. And in that case, we did not require to restrict the Killing spinor, so we are preserving in this way 4 supersymmetries, which is 1/6 in the counting of ABJN, what we wanted to have. So just as a check that using dimensionless mixed interpolating parameter is the right thing to do. We computed like correlators out of these 2 examples of boundary conditions I discussed so far. So in the type 1, okay, how do you compute correlators? You have to solve the Klein-Gordon equation with boundary conditions when you turn on sources. We are now not solving this equal to 0, but equal to a source. And then you compute the on-shell action and take derivatives with respect of the sources, and then you compute the correlators. In the case of the type 1 mixed boundary condition, what you see is that the correlation function you get is something that is not the correlator of a conformal field theory, as you might have expected, because you are introducing this dimension full parameter. When you do that for the type 2 case, yeah, the introduction of the time derivatives, so it modifies how this omega appears here. So at the end of the day, so the dependence of this coefficient just parameterized, and then what you get is when you have this type 2 mixed boundary condition in which this coefficient in the interpolation is dimensionless, what you get is a conformal, a correlator for a 2-point correlator, which is perfectly consistent with conformal symmetry. So, okay, we might think that this is what we were looking for, but still there is a twist we have to make on this condition, because if you think carefully, what this type 2 boundary condition is interpolating between beta equal to 0, which, as I said, is the vanishing of the normal derivative of the scalar field at the boundary, with alpha dot equal to 0, which is like saying, okay, at the boundary, my scalar field will be constant, but I am not specifying the value of this phi naught. So it's like this type 2 is interpolating between Neumann and some smearing of Dirichlet boundary condition. So to interpolate between Dirichlet and Neumann, we have further to fix phi naught, and the way we could do that was just, instead of considering the alpha dot plus beta, we have like the integration of that condition. So this fixes the value of phi naught, and it's a perfectly good boundary condition. We could derive the boundary term to realize it, and then, okay. So this is like this type 3 mixed boundary condition is like it's ticking all our requirements, and if you wish, it was the main result of our paper. So let me just summarize. It preserves 4 supersymmetries, which in the counting of ABJM is 1/6 BPS. They interpolate between Dirichlet and Neumann boundary conditions, and this interpolation is in a way in which the parameter that is interpolating is dimensionless, so you expect a conformal symmetry to be preserved, or scale invariance So this is our proposal for the dual description of this supersymmetric family of Wilson loop interpolating between the fermionic, the 1/2 VPS, and the bosonic 1/6. So we did a check, a one loop check so you can compute the one loop correction to the partition function in terms of the vacuum energy. And then you expect this to be independent of chi, because we said that the expectation value of this family of Wilson loop did not depend on the deformation parameter. And in spite of using this chi-dependent boundary condition, when we computed the vacuum energy, we checked that this is independent of this parameter entering in the boundary condition. So let me just go to my summary and to raise a few questions. So, okay, if you want to take out, I mean, if you want to, if I had to say a very basic conclusion is that we learned the usual ADS-CFT lesson. Whenever you would like to do a gravity computation and interpret it correctly as a field theory result, you better do a detailed analysis of the boundary conditions in the gravity side. What we did in our example was to consider mixed boundary conditions in ADS2, and we claim that you can use them to describe either renormalization group flows in this one-dimensional defect or marginal deformations of it. And in particular, we had this supersymmetric family of Wilson loop with this zeta parameter, and then we claim that what we named as type 3 boundary conditions in ADS2 is the correct proposal to describe them holographically. Okay, and then there are a few questions you could ask. Whenever you have these boundary conditions with a dimensionless coefficient, are they always exactly marginal? Okay, you need to consider the completion of the theory. In the looking for the good boundary conditions, we found this type 1. We said they are not enough, they don't have enough supersymmetries, but they are there. So the question is there any Wilson loop describing this other kind of boundary condition, or can we extend this analysis to of mixed boundary condition with dimensionless parameters to higher dimensional spaces? I don't know. There are many other questions, so I think I'm over time, so I will stop here. Thank you very much.
Okay, questions? David?
Yes, very nice talk. I have a question, which is, there's also Tooth Wilson loops. Is there a similar story that you can do for Tooth Wilson loops, or is that something that can't be done with the current methods?
No, I guess that as long as, yes, you could do the same, as long as you have a description in terms of fluctuations in an ADS2. You probably can try to do a similar analysis. Yes, still, I mean, another thing that okay, then you have to think of what could it be, the interpolating parameter, what would it represent in your Toff loop? But I don't know what, I mean, if this addressing your question, or if you have something more concrete in mind, David.
Well, usually S duality turns the fundamental loop of an equatorial Mills into a Tooth loop. But I wanted to understand a little bit better, what do we know about these operators more precisely?
Right. Yeah, well, I don't know. I have to think about it. What would it be the description of this Toff loop in terms of excitations in an ADS2 worldsheet? But yes, I haven't thought about it carefully, so let me think about it, and maybe we can
okay, thank you.
You're welcome.
Okay, now questions by Jeremias.
Hello.
Hi, Jere.
Yeah, I have a very basic question about these type 3 boundary conditions, because they seems to be non-local in this T parameter, because they are integrated. Is right?
Yeah, that's exactly right. So
can you use it to compute the correlation function? So you, or in other words, will you expect to get a non-local expression for the correlation?
I mean, as I said, I mean, that's absolutely right. I think whenever even this one, what we call type 2, sorry, that involves a derivative, it's in some sense non-local. I think it was discussed in a paper by Marolf and Ross. And as you said, I mean, it's a non-local boundary condition, but then you can use, I mean, as I said, you can compute, you can work it out what is the boundary term leading to this boundary condition, turn on a source, compute the correlation functions, and then you don't get any non-local fancy thing. What you get in this other type 3 case is like the sorry, what it is? It's like the derivative of this. Instead of the logarithm, you are like, okay, you get something like this second line in this, but this is perfectly local, and I don't know. I mean, it is true that the boundary condition is non-local, but I don't know if this has a direct consequence on the field theory correlators. I don't see any. I mean, what we obtain are just perfectly normal correlators for a CFT for operators with scale dimensions, say delta equal to 1 in that case.
But sorry, you get that second line in the bottom for any value of chi or just
in type 3, yes. So here, I mean, I was looking for an expression. If you do this computation with type 3, what you get is a correlator, which is for any chi, you get like a coefficient like in this case in front, but then the correlator is 1 over T1 minus T2 squared. And then that's the usual correlator in a CFT for operators of dimension delta equal to 1.
Interesting. Okay, thank you.
You're welcome.
Okay, now Carlos Núñez.
Diego, one quick, and then I let Leo ask. So in all these cases, you wrote, for example, in the n equals 4 case, the action, or at least you say that there is a CFT1 on the defect, right?
Yes.
The question is, can you write an action for that CFT1? Certainly, you can calculate observables like the free energy of the thing, as you show in the second case with the BEV of the Wilson loop. But could one write an action for that, a weakly coupled action, and if that would have any meaning?
Yes, okay. At least in the case of n equal 4, or at least this interpolating Wilson loop in n equal 4, I remember that there is a paper by Carlos Hoyos in which he tries to derive an action for this defect field theory in the line, but I don't remember by heart the details. I can have a look and see if I can say something else. But yes, but in general, no. I mean, what I have is just a definition of the theory through the conformal data. I mean, the correlators of the excitations along it. But it's a sensible question you could ask, and as I said, I mean, I remember that paper by Carlos Hoyos in which he was asking exactly that kind of question in n equal 4.
Yeah. Very brief one. In the n equals 4 case, you mentioned with this zeta interpolating parameter that when zeta is equal 0, you have the Wilson loop, the usual Wilson loop, right? With the
ordinary one.
But if zeta is equal to 1, is the Wilson-Maldacena. Tell me if I'm wrong. The Wilson-Maldacena is supersymmetric. The Wilson is not.
Right.
So it's a very nice odd flow, because in the UV you have no SUSY, and in the IR you have SUSY, right?
Yes.
It's a very nice oddity. I know other examples, but they are odd. I just wanted to mention that. Then.
No, that's right. So I mean, when I first, I mean, I don't know why, but intuitively you would expect it the other way around. But it is true. But then it is also true that there are examples in which you have a UV that when a renormalization group flows that take you from a non-supersymmetric UV to a supersymmetric infrared fixed point. That's true. That is I don't know.
It's a bit odd.
It's a curiosity,
okay.
but I mean, I don't see any reason why it should
Why not?
be.
Exactly.
Yeah, why not?
Thank you very much, Diego. Muy
Very
bien.
welcome.
Okay, so I'm afraid I have to leave Leo's question to the discussion session. Sorry, Carlos. Okay, so we have a 5 minutes break now.
Hello, Victor. Can you hear me? Hello?
Yes?
Victor, I'm Martin Schweringer.
Yes. Hi, how are you?
How are you doing? I want to share my screen, but
Okay.
Can you see my screen? No.
Yes, it's all right.
And what about now? Can you see it?
Yeah, now it's okay.
Okay, thank you very much.
All right. Okay, we can now start the third talk given by Martin Schwellinger from Universidad Nacional de La Plata. And I was going to talk about the hadron structure from string theory.
Okay, thank you very much, Victor, for the presentation, and thank you, the organizers, for the invitation to this very nice conference. I'm going to talk about hadron structure from string theory, and the work that I'm going to present. Sorry, I have a problem. Okay. Okay, here. The work that I'm going to show you is mainly describing this series of papers, particularly in these two papers indicated here by my students, Nicolas Kowensky, Gustavo Michalski, and David Horin. Yep. The idea of the talk is the following. I want to describe spin 1/2 hadrons using type 2B superstring theory on ADS5 cross S5, and with an infrared cutoff. Sorry, someone is asking me to be admitted in the talk. This is the reason, because I have some problems here. Sorry. Maybe you can do it, Victor. And then I want to show you how to calculate structure functions for large values of the biochem parameter x using supergravity in this range. I'm going to explain it later. And also, I want to show how to calculate structure functions for small values of the biochem parameter using superstring theory amplitudes in this parametric range. I will explain it later. And finally, in the exponentially small values of the biochem parameter, where the Regge physics becomes important. And then we're going to see certain techniques called holographic Pomeroy techniques. And finally, I will show you some comparison with the experimental data from COMPASS collaboration, which runs at CERN. So when we are talking about the structure of hadrons, we think about this kind of experiment. Deepness scattering, DIS, and is represented by this Feynman diagram over here, where you have basically, let's, to fix ideas, this can be a proton, and this carries an initial full momentum p mu, and then you have an electron here, which initial momentum k mu, and a final lepton, which is the only thing that is going to be measured because the process is inclusive. The idea is that the proton is going to be probed by this virtual photon, and after that, the proton fragmentates in a lot of new hadrons, which are not going to be measured. The only thing that is going to be measured is the kinematical properties of this outgoing lepton over here. So basically, the differential cross-section for this process is written in terms of this azimuthal angle of the reaction, and these two things over here, which are Lorentz invariant quantities. One is the fraction of energy loss of the lepton, defined over here. And then we have this parameter, which is very important, and this is the biochem parameter, defined this way. And its physical range goes from 0 to 1, being 1 the case where the process becomes elastic. So the point here is that since this is an electromagnetic process, we have the electric charge, and then over here there is the more important thing, the contraction of these two tensors. One is a leptonic tensor, written over here, and it's very easy to be calculated in terms of just quantum electrodynamics. But the second piece, this tensor over here, is the thing which is very complicated to calculate, because it contains two electromagnetic currents. This is basically the commutator of two electromagnetic currents inside the hadron. So this is the initial state of the hadron, the momentum and spin or helicity, and this is the final, the outgoing state of the hadron. So this is very complicated because it contains soft processes in QCD, which are in the regime where the theory is strongly coupled, obviously. So basically, this is the part where the ADS-CFT duality enters. This process, typically in quantum field theory, is related to the forward Compton scattering amplitude. And the relation is through the so-called optical theorem. And the relation specifically is this: 2 times the imaginary part of the Compton scattering amplitude gives you, basically indicated over here, this T mu nu has nothing to do with the energy momentum tensor, but this is just the amplitude of the forward Compton scattering. And then if you take 2 times the imaginary part of this quantity, what you get is just the W mu nu tensor that we want to calculate. So in the case of spin 1 hadrons, the hadronic tensor is written in this way, separated in a symmetric part and an antisymmetric one in terms of the exchange of these two Lorentz indices. I remind you that we are talking at this moment just on a quantum field theory in 4 dimensions, and then this is the usual 4-dimensional Minkowski spacetime. And the structure of these two parts of the tensor are given by this series of rank 2 tensors, which are Lorentz invariant, and then you have over here these encircled quantities, F1, F2, F3, and also if you look at the bottom, G1, G2, and then G3, G4, G5 are the so-called structure functions. These functions are scalar functions which contains all the information about the structure of the hadrons, and they are functions of the Biot-Chem parameter and the momentum transfer Q mu of the virtual photon that probes the structure of the hadron. So we are not considering specifically in the calculation that I'm going to show you from the holographic point of view, QCD, because we don't have actually the holographic dual description of QCD, even not in the Largian limit. So the thing that I'm going to consider is the Largian limit of SU n equal 4 superemia theory. And I'm going to introduce by hand an infrared deformation that I'm going to explain a bit later. So the philosophy is the following. We don't have the dual description, the holographic dual description of QCD itself, but we can describe certain properties of QCD itself. I can comment more in the questions if you wish. And schematically, if you look at QCD, there is a picture which is interesting in order to discuss what happens in terms of the two variables on which depends either the hadronic tensor or the structure functions, which is the logarithm of the inverse of the Biot-Chem parameter. Remember that it goes from 1, this is when this logarithm over here is 0, basically is because x is 1, and then over here we can go up and have the smaller values of the Biot-Chem parameters. Yep. And this is the non-perturbative region because this is taken in the smaller values of the logarithm of the square of the momentum transfer of the virtual photons. So this is a strongly coupled region that we want to describe. And I'm going to show you that there are 3 regions in which we can do some approximations to deal with the problem from the holographic point of view. One region involves supergravity, type 2e supergravity. The other region needs to include string modes, excited string modes, and the third region is a bit more complicated, and I'm going to discuss something called holographic Pomeron for that region. The rest of the diagram is very interesting. It depends on a description in terms of QCD methods, and but I'm not going to describe it here today. The holographic dual description, as I said before, in terms of type 2e supergravity and type 2e string theory, can be separated in three regimes. The regimes are basically, well, they depend on the relation between the 't Hooft coupling of the field theory and the Biot-Chem parameter. And this picture over here can explain it better. So at least for the first parametric region. So this is a typical Witten diagram. And over here we have the boundary of the anti-zeta 5 dimensional space. Here we have the interior, and the idea is that we are going to insert over here the operators, the current operators of n equal 4 superior theory on the boundary. And the reason is because we want to calculate the correlation function of these two things. And the idea is that once we insert those operators at the boundary, they induce fluctuations on the metric, and the consistent fluctuation on the metric is the off-diagonal one, which can be parameterized in terms of this gauge field, which takes values on the anti-zeta space, and these are the Killing vectors on the phi sphere. So basically, in principle, we have non-abelian gauge fields over here, but it can be shown that consistently we can just turn on one of these non-abelian components and reduce that to an abelian gauge group. So this is the thing that one typically does. So this is the propagation of this gauge field over here reaches some point in the interior where the interaction concentrates and then reacts or interacts with a D Latino field. The D Latino has an incident state, there is an intermediate state, and then an outgoing state. And it represents holographically the forward Compton scattering process that I mentioned before. So basically, if you rotate this diagram 90 degrees, what you get is this pictorial representation where here we have the boundary of anti-de space where the physical process actually occurs. And then over here we have the interaction region for the holographic dual description. And then here we have the infrared cutoff. Okay, if you look at here, what we have is the 10-dimensional Mandelstam variable. This is very important for the description. If you write it down, what you get is, well, this is the expression which defines the 10-dimensional Mandelstam variable, but then it can be written in terms of this inequality, keeping here only the 4-dimensional piece. And then what you get is an inequality which can be expressed in terms of the Berken parameter, the alpha prime constant of a string, and this is the string constant, and this is a typical number of D3 branes on this background. And basically what you get is this particular condition here. So basically if the Berken parameter runs from 1 to down to the inverse of the square root of the 't coupling, defined in this way, what you get is that basically only supergravity states, as indicated by this inequality here, are important for the description of this diagram. So basically, this is what happened within this parametric region. Yep. This was a proposal of 18 years ago by now by Polchinski and Strasler, and a very important paper at that time. And basically, they did a calculation using the minimal coupling in the interior, the minimal coupling between the fermions and the gauge field within type 2 supergravity. And then they obtained this relation is very interesting because this relation contains an information similar to the so-called Calan-Gross relation when you consider the perturbative regime of a theory. And on the other hand, the explicit functional form, depending on the momentum transfer of the virtual photon, is very important because what you can see here is the expected behavior in terms of the power of the twist of the incident hadron. The twist is defined as the difference between the scaling dimension minus the spin. And basically, they introduce by hand an infrared scale here, yeah? And this is what one should expect from a quantum field theory in the perturbative regime. So the dependence on X for this particular parametric regime that I was mentioning is given by this expression, which you can see that if X goes to 1, basically you have 0. In this picture, we have the behavior which is 0 approaching 1. And then obviously, because this positive power of X over here, for X going to 0, it goes also to 0. So basically, using exclusively the supergravity calculation, what you get is always a sort of bell-shaped curve. But 7 years after that, Gao and Xiao did a calculation using just bottom-up approach in which they consider on the top of this minimal coupling the Pauli term. I will comment in one moment about that. That was a kind of bottom-up calculation, but they managed to obtain the rest of structure functions, obtaining an extension of the Calan-Gross relations in this way. So basically, they get also bell-shaped curves, and what happens in nature is that, as you may know, basically, as you consider smaller values of the Berken parameter, since the Berken parameter is a fraction of the momentum carried by the eventual partons that constitute the hadron, the idea is that there are much more partons once we consider smaller values of X, and therefore the expected behavior of these structure functions should be increasing as you decrease the value of the Berken parameter. So basically, much recently, what we did was a calculation with David Horin and Gustavo Michalski this year, in which we considered two new things in a sense. One is a precise incorporation of single trace spin 1/2 operators of n equal 4 superjammer theory. And the kind of operators that we consider are the ones that I'm calling here O6, depending on this parameter K. K basically is the power of the real scalar field here. These are the gauge in the field theory, and these are the gauge fields. And the O13 operators are defined this way. So basically, they are connected through the ADS-CFT dictionary with Kaluza claims, which comes from the reduction of type 2 supergravity given in this paper, Kim Romans and Banyan Houston paper, a very old paper, in which they present this mass spectrum. We are taking this line over here, which corresponds to the Kaluza claim modes associated with the operators that I call O6, and the other line here, which contains these 4, 20, and 60, which corresponds to irreducible representations of the SU4 R-symmetry group of n equal 4 theory, basically. When you connect with the operators that I just mentioned, they are the corresponding Kaluza claim modes associated with the O13 operators. So the second thing that we have done is the following. We have done a fully consistent reduction on the phi sphere of type 2A supergravity for the fermionic sector, including the interaction. And then this is the minimal interaction. And then there are two additional contributions, which are of the form of the Pauli terms. And then the idea is that considering these interactions, the previous Callahan-Gross relations, which are extensions of the Callahan-Gross relations, reduced to this number of relations. So this is something more precise that we obtain. And then something very interesting is that if you consider the states over here, basically the different Kaluza claim modes, what you obtain are different curves depending on the quantum numbers associated to each group of these states. So, but in all the cases, what you get are bell-shaped curves for the supergravity region description. So you can go further and go to the 16-star representation of the SU4, and then what you get is a more complicated structure here. So this is 1/3 of the story. The second piece of information comes from the parametric range of the Bjorken parameter, which is in between the inverse of the square root of the 't Hooft coupling and this exponentially small region. Yeah, and for this region in particular, what you get is that if you do a similar calculation as I showed you before, what you get is that the Mandelstam variable in 10 dimensions is of order of the square of the Planck mass, basically. So string states are very important in this description, so we have to include them. But the problem is that due to the fact that we have Ramon fields, we don't know how to reach the scattering amplitudes. So, and then what we're going to do, following Porczynski and Strassler on that paper, is do certain approximations which are very interesting for this present case. So let me see. So before going to that specific calculation, let me recall that from the pure four-dimensional quantum field theory analysis, this small region, which, as I just mentioned, it corresponds to this parametric region. If you just consider the momentum transfer of the virtual photon fixed, then since this value of x is very small, yeah, then if you put it here, basically what you get is that the four-dimensional Mandelstam variable is very large, and if you do a very simple calculation, the T-channel Mandelstam variable gets 0, exactly 0. So basically in this region, for the four-dimensional quantum field theory, what is important is the T-channel. What about the 10-dimensional analysis of the dual model? Well, in that case, the analysis is more subtle, and then what we have over here is a relationship between the 10-dimensional and four-dimensional variables, given in this way. And basically what you have is these are the 10-dimensional S and T variables annotated here with a tilde. And over here, if you see, we have a first term, which is just a scalar, like here, yeah, and it contains a 4-dimensional variable and the redshift factors. And over here, what we have are differential operators that by now we are going to neglect them because they give contributions to the order 1 over the square root of the Tooth coupling. So basically, in the 10-dimensional stuff, the description also has very small values of t, the 10-dimensional variable, Mandelstam variable in the t channel, but it's not zero. It's not exactly zero. We can take a limit in which this is zero, but we're going to consider two regions in that case. I'm going to show you in a moment. So basically, now I'm presenting here which are the Witten diagrams that are going to contribute in the T-channel description. There are two types of Witten diagrams. This should be the boundary of the anti-situ space. This also the boundary. And then one of the diagrams contains the propagation of a graviton between the fluctuations of graviton here and the dilatino. And the other one is going to contain here something which is a gauge field composed by the linear combination of a vector fluctuation of a graviton minus a vector fluctuation of the four-form Ramon-Ramon potential. So basically, this is a Chern-Simons interaction over here. The first diagram contributes to the structure functions of the symmetric type, and the second one contributes to the anti-symmetric. So basically, this is a pictorial representation of the T-channel. So the idea now is I'm going to follow here the paper of Polchinski and Strassler, and the idea is the following. We don't know the form of a string theory scalar amplitude in curved space because this is Ramon stuff. So since the interaction within the bulk is going to be concentrated in a very small region of the size of the Planck length, so basically this is very small in comparison with the radius of the anti-situ space, and then what they proposed, Polchinski and Strassler, was to take just a flat 10-dimensional string scattering amplitude of two gravitons on the boundary and two fermions, yeah, the two dilatinos, and then integrate this amplitude over the curved spacetime. And basically, the flat scattering amplitude is given by the product of these things. This function here contains the gamma structure of the amplitude, and this contains basically the kinematic parts of the bosonic open string and the fermionic open string. This is a typical Kawai, Llewellyn-Smith tie formula. Basically, this is the way in which these two functions are written just in terms of Mandelstam variables in 10 dimensions, and also in terms of the closer string graviton and closer string dilatino polarizations. So basically, if you do some calculations, some algebra, what you obtain is this, and basically what you can extract is a symmetric contribution. The symmetric contribution gives you this expression, and you have to compute the imaginary part of this function g here. And the symmetric contribution is associated, as I told you before, with the propagation of the graviton here. And the anti-symmetric contribution contains this structure, and then it contributes to the propagation of this gauge field. So basically, what we have over here are 4-point vertices, which contains the information when you basically take the limit of t tilde going to 0, which implies that you join these two vertices in one single 4-point vertex, yeah, in the effective description. So basically here we have to take in order to finish the calculation, we have to take the imaginary part of effective action, and then in order to do it, we take the function which contains the gammas, yeah, the gamma structure, and then we have to take the imaginary part and also take the limit t tilde, the Mandelstam variable, in 10 dimensions going to 0. So for the first thing, I mean, this imaginary part gives you this sum over excited string states, and this part over here you can reduce just to 1, because we are considering here the limit t tilde going to 0. If you do it, you can extract doing kind of lengthy calculation, these structure functions with certain new Calan-Gross relations. But it is also interesting, the second piece of information, the part that you have to consider whenever you consider the exponentially small region in terms of the parameter, the Biochem parameter. This is the region in which the regiophysics becomes very important, and this is the so-called description of the description in terms of the so-called Pomeron. So basically, the consistent treatment of the differential operators here implies the propagation of a region or a full Regge trajectory, which is called the holographic Pomeron. This is a Regge trajectory of gravitons here, if you consider the symmetric part, or the Regge trajectory of the gauge fields, if you consider the antisymmetric functions. So basically, the name Pomeron comes from the fact that you have an amplitude which is very similar to the thing that you have in actual QCD, where the description has this integration over here, and then you have two factors which are called impact factor, and then you have the BFKL Pomeron in QCD. But here, what we have is something different, which is a Pomeron obtained a few years later, a few years before, by Brouwer, Polchinski, Strassler, and Tan. So basically, from this, you have to take the imaginary part, multiply by 2, you get the W mu tensor, and then you can extract structure functions. This structure, okay, we have obtained these two expressions, but the first one was obtained previously by Brouwer and collaborators, and it has three free parameters. And this one, the one which we obtained for this G structure function, contains just one free parameter. So these are different structure functions, obviously. And okay, let me show you what happened with the first structure.
You have 5 minutes left.
5 minutes. Okay, thank you. So basically, if you look at this, picture over here, what they did, I mean, Brouwer, Durick, Sarchevich, and Tan, is the following. They fit this expression over here with three free parameters, as I said, against the data. The data coming from this experiment, H1 Zeus at Hera in Desi, in Germany, and basically it had 249 data points. And basically what they did, what they got is that this chi-square per degree of freedom of 1.04, yeah? And this is for the region in which x is very small, basically, yeah? The values of x are, this is a logarithmic scale in this axis, and it's very small, yeah? So this is basically the exponentially small region. And then what we did is the following. We took our G1 function. The G1 function measures, if you look at the proton, it measures the asymmetry of the spin in the proton. And basically, these are data points obtained by this collaboration, COMPASS at CERN, between 2015 and 17. And these are the data. If you look at here, the values of the x are really small, yeah, until, okay, up to here, but over here, very small. And look at, with just one parameter, here we have 29 points, and using just one parameter, what we have is this fit, which well, it has a chi-square per degree of freedom of this value, which is very acceptable. And this was very nice because we have now a kind of complete description for small x region using these techniques of holographic duals. So, well, I think I will stop here. Thank you very much.
Okay, thank you. Questions? Okay, David?
Yeah, you did the calculations with a Gravitino, I think, or the Dilatino, which is...
Dilatino.
Yeah. Yeah, but that is a closed string state. And I would assume that if you're going to match to the proton, you should be matching to a D-brane, to the how do you call it, the Witten vertex, for example. Or
right,
like
I understand your question, yes, yes.
Have you thought about that? How to do
Well,
it with brains?
you know, the problem is the following. This is just a mimic of what happens if you represent this state of, if you represent the proton as a D Latino. This is not a correct representation, of course. What you say is correct. The point is the following: if you consider the Witten baryon vertex, the baryon vertex has a mass which scales with n, and then what you have is that there is a kind of non-dynamical representation of the proton in that way. This is the reason because we cannot do it using that representation. Maybe you can do something using skirmins in a way in which Sakai Sugimoto in that D3, D4, D8 anti-D8 model presented. But I don't think that you can apply these techniques with the baryon vertex.
Okay, thank you. I'll think about it more.
Okay, next question from Carlos Cardona.
Thanks, Victor. Hi, Martin. It's nice to see you again, even though
hey, hi, Carlos.
This camera. So I have a couple of maybe one technical question. So when you use these Witten diagrams, it looks to me. So I missed this point. It looks to me you are using the flat space. So you put instead the flat space S matrix in 10 dimensions. Is that what you're doing, or you're computing the actual Witten diagrams?
In the Witten diagram, when I show you the Witten diagram, I actually use the usual ADS-CFT calculation. I haven't taken anything flat in the Witten diagram calculation, in the supergravity calculation. But then when I move to the other regime, in that regime I consider the flat scattering amplitude, and then I convolute it somehow with a curved space.
Okay, so from the QCD perspective, this BFKL kernel that is used, when Reggie, so this guy has computed by using Reggie theory and the integrability of QCD in that region.
Right.
So the methods that you use in the dual description are something similar to that. There is
It's
equivalent Reggie theory from.
Yeah, exactly. It's the same. It's the same thing, but translated to the holographic dual description. Instead of having let's say a rigid trajectory of QCD particles, what you have is a rigid trajectory of gravitons, and that thing is the thing that gives you the symmetric contribution. And on the other hand, the anti-symmetric contribution comes from the rigid trajectory of gauge fields.
Can we do the same in the A canal?
Yeah.
I see.
Yeah.
I see.
Yeah.
And is this rigid theory related to the rigid theory developed by João Penedones?
Yes, absolutely.
Miguel
Exactly. I haven't mentioned that because I didn't have time, so I was running.
Cool. All right, maybe I can ask you more during the discussion section.
Okay, welcome.
There are a couple of questions following.
Thank you, Carlos.
Thank you, Martin.
Carlos. Okay, next question from Diteramont.
Hello, Martin. Long time no see. I saw you.
Nice to see you, G. Nice to see you, G.
Nice to see you. Very nice talk.
Thank you.
If I understand well, you have applied this extended Wolschitz-Strassler method, and very nicely. But you are really describing the LAWGH region.
Yeah, at the end, this is the thing that I did.
Okay.
At least in the pictures, yeah, in the fittings.
Are you planning to extend this to LAWGH?
But okay, LAWGH is a region. Let me show you very briefly. LAWGH is what I mean by LAWGH is x between the square root of the inverse of the 't coupling and 1. Yeah, this is LAWGH. What I mean. Do you mean that? Do you mean that?
Yeah, well, I really mean, yeah, going into the large X limit. Now, because you show a result by Polchinski-Strasser.
Yep.
That I recall they found 1 minus X to the tau minus 2.
Yes.
In the paper.
Yes. Yes.
Now, it happens that this is really wrong because it does not obey the inclusive exclusive counting rules. And let me just tell you, in case you adventure yourself into the very large X region, why is the reason why?
But sorry, for small X, that is right. I mean,
for a small X, there is no problem.
Yeah. But for large X is different. We don't have a Pomeroy description for large X. We have the supergravity dual description. Yeah, it's totally different. Yep.
But yeah, exactly. But the behavior found by Polchinski-Strasser does not reproduce the counting rules, which is 1 minus X 2 tau minus 3. Because otherwise you have a nonsensical result. For example, for the pion, this gives you a constant behavior near X1 because it's tau minus 2. Well, the problem.
But sorry, in which region you say that it doesn't reproduce
the very large X region?
Okay. I'm fine with that. Yep.
Good. So what happens? It is something very interesting, is that in holography it really gives you the t dependence or the q squared dependence from factors or amplitudes. But this is the integral of some X function. The problem is that this function is not uniquely defined, because essentially this is an Euler beta function, so it's reparametrization invariant. And in fact, what happens is that you take really care of the problem and you examine the large X behavior, you will find, sorry, that precisely this term by Polchinski and Strasser, the 1 minus X to the tau minus 2, vanishes. It's zero, should be 0. And then the next term in the expansion gives you the right inclusive exclusive counting rules. So this was noticed lately. There is a PRL paper to 2018 by myself and the HLFHS group. If you want to take a look at the discussion.
Yeah, thank you.
There.
Thank you.
Good.
Thank you. This should be appropriate for the description of this region, the pictures.
Absolutely.
Yeah,
because
I will have a look.
Exactly,
yeah,
because this region is governed by the QCD counting rules.
Yeah.
Exactly.
So thank you very much, Guy. Thank you.
Okay, and congratulations for the nice work.
Okay, thank you.
Bye-bye.
Bye.
Okay. Next question from Carlos Nunes.
Martin, in the interest of time, I'll ask a very short one and keep the others for the discussion.
Okay, Carlos.
At some point, you, in calculating a diagram, you calculated a diagram where a graviton was propagating, and then also was propagating a mixing between the graviton and C4, right? And a fluctuation of C4.
Yes, exactly. Yep. Yes.
So the question is, if that is going to give something observable, how come the fluctuation of C4 that is not gauge invariant, I can always shift it by a gauge transformation, how come that fits into an observable?
But this is an internal line, you see?
Yeah.
This is an internal line. You cannot observe, there are no external fields like that. Over here, this is just the usual off-diagonal fluctuation of the graviton, this one and this one. And these are the only ones which are connected to the current operators on the boundary. These are the only things. And
so
this
your point is that if there I put the fluctuation that you put plus a gauge transformation of it, I will not make any difference in the calculation.
No.
Okay. Thank you.
Thank you.
Okay. No more questions. Then we can have a 6 minutes break now.
Thanks.
Thank you.
Stop share. Okay.
Hi, Berta, are you around? Do you want to check whether your slides are working and all that?
Hola, Damián. Sí,
Hola,
podemos.
hola.
A ver. Pantalla. Ok. Share screen. Ok. ¿Puedes ver mi pantalla?
Sí, perfecto.
A ver.
¿Quieres ir a full screen y chequear, pasar los
Screen.
slides y todo eso?
¿Cómo?
Sí, si vas a full screen y tratas de pasar los slides y chequear que todo funcione.
Ahí.
Ok.
Aquí yo veo una... No sé cómo deshacerme de esto. A ver.
Pero yo lo veo bien, ¿eh?
Sí, sino que acá, no sé, la ventana del Zoom se me pone igual encima del full screen. Entonces,
Quizás cuando haces share screen puedes elegir solamente compartir la ventana. En lugar de toda la pantalla, solamente el PDF.
Ah, a ver. Ahí me ves. Ahí, ok. ¿Me avisas cuando tengas 5 minutos?
Sí, seguro.
Ok, gracias.
Es media hora en total y te aviso los 25.
Sí. Sí, igual yo tengo acá también mi celular, lo voy a poner cuando comencemos para irlo viendo.
Ok. All right, maybe we can start. Welcome everyone to the last session of this very nice workshop. Our first speaker for this session will be Berta Cuadros Melgar from University of Sao Paulo. And she will be telling us about an analytical correspondence between shadow radius and black hole quasi-normal frequencies. Berta, all yours.
Thanks. First of all, I would like to thank Elena and all the organizers for their efforts to put forward this wonderful idea of having a virtual conference. So this work I'm going to present today is something a bit different from what has been discussed all these days. And this work was made in collaboration with my colleagues Rodrigo Fontana from the Federal University of the Southern Border and Jefferson de Oliveira from the Federal University of Mato Grosso. And this is the address of the archive where this work is. And so the idea of this work is to establish a correspondence between the shadow of a black hole and the quasi-normal frequencies corresponding to some kind of perturbation of this same black hole. Now, let me tell you the plan of this talk. I'm going to begin giving some introduction in order to see the motivation why we want to do this work and also the things that have been done before. Then I'm going to talk about the geodesic part of this shadow radius of a black hole and also the quasi-normal frequencies. And I'm going to join these two concepts in order to make this correspondence. And then I will give some examples in order to illustrate this correspondence. One of the examples is in G dimensions, that Angerlini black hole, and the other is a four-dimensional black hole with an anisotropic fluid. And finally, I will summarize my results and also give some conclusions. Okay, so first of all, talking about quasi-normal modes, we all know that they appear as a response to field perturbations around compact objects. And among these compact objects, we can consider the black holes, that is the subject that we are going to study here. These quasi-normal modes are characterized by quasi-normal frequencies. This number here that is a complex number, that's why these modes are called quasi-normal, where the real part of this frequency is related to the oscillation and the imaginary part of the frequency is related to the damping of this oscillation. The good thing here is that these complex frequencies only depend on the geometry that we are perturbing and also on the field characteristics. I mean, if we consider a scalar, a vector, a spinorial, or even a gravitational perturbation. Now, talking about the shadow side and the geodesic things, some years ago, Cardoso and his colleagues proposed some equivalence between the quasi-normal frequencies and some geodesic quantities. In particular, they proposed that the real part of a quasi-normal frequency is related to the angular velocity of null geodesics. And also, the imaginary part of this frequency is proportional to the Lyapunov exponent for these null geodesics. I can remind you that these Lyapunov exponents are a measure of the average rate at which nearby trajectories diverge or converge in the phase space. In particular, if these coefficients are positive, we know that there is a divergence in these trajectories, so these trajectories are very sensitive to the initial conditions. And now this hypothesis has been revived due to the black hole shadow reported by the Event Horizon Telescope. And the main objective of this work was to make this missing connection between the quasi-normal frequencies and the shadow radius. Okay, so let me talk about this correspondence. So let's begin from the shadow side. If we consider a spherically symmetric d-dimensional black hole like this here, where this part is the angular part of the black hole, we can study the photosphere orbits here. When I talk about photosphere, I am referring to the following fact. If a light ray starts tangentially to such a photosphere, it will stay on a circular path with radius RPS, that is this photosphere radius, so a fixed radius forever. So if we employ, for example, a Hamiltonian or a Lagrangian formalism in order to study geodesics, we can find that the photosphere orbit obeys this kind of equation. Now, the idea is to use this equation that will give us the photosphere radius in order to define the shadow of a black hole. The shadow basically is a dark disk whose boundary corresponds to light rays that asymptotically approach the photosphere. So this shadow radius, as seen by a distant observer, can be defined in this way. This R over the metric function, square root, evaluated at the photosphere radius. Now, from the quasi-normal mode side, we can consider a general perturbation in this spherically symmetric background, and the equation of the perturbation can be decoupled from the angular part, and the remaining equation can be written in a Schrödinger-like form, like here. And here we see this x coordinate, it's a new coordinate, the so-called tortoise coordinate. And here we have a potential that encodes all the information about the space-time geometry and the kind of perturbation that we are using to perturb this background. So in general, for any kind of perturbation, this potential can be written in this way, where here this L is the multiple number associated to the angular momentum of the perturbation. And this is important because the correspondence that we found is a correspondence that works for the Eikonal limits, so for high multiple number. Now, in order to deal with this kind of potential and due to the shape it has, we can employ the semi-analytical WKB approximation in order to find the quasi-normal frequencies corresponding to these perturbations. So how this WKB approximation works? Let me show you here this plot. In principle, we begin with a Schrödinger-like equation like this that I am showing, where this Q of x makes the role of a potential, and this function Q is plotted here. In fact, it is minus Q, what is plotted, and the requirements that we need for the potential to fulfill is that it must have a peak, and at the region of the event horizon and the infinity in the R coordinate, notice that here the plot is in this tortuous coordinate, so minus infinity corresponds to the event horizon. In these two regions, the potential must go to a constant, not necessarily the same constant. So the motivation of WKB approximation in this case is the similarity between the equations of black hole perturbations and the one-dimensional Schrödinger equation for a potential barrier. So the idea is to consider this function psi here, in the region 1 and region 3 and approximated by linear combinations of incoming and outgoing WKB functions with real frequencies. These 2 points here, x1 and x2, are turning points of our potential. And the idea for the method to work well is that these 2 points must be close and near to the peak. So the method basically matches the 2 exterior solutions in region 1 and region 3 across these 2 points x1 and x2 simultaneously. In the region 2, this function q of x is expanded in a Taylor series around this peak, and an asymptotic approximation to the interior solution is connected to the exterior solutions. So in doing this, we can find an equation like this last equation I am showing. Here, Q0 represents the value of the potential at the peak x0. And we also have here the second derivative of this potential evaluated at the peak. Notice that since we suppose a time dependence of this perturbation as being exponential of minus imaginary omega t, this frequency is inside this Q0. And these functions lambda and omega, they depend on higher derivatives of the potential evaluated at the peak, and also on this n, that is an integer number, the Overton number for the oscillation. Okay, now that we know how this method works, we can apply it to our case. So, using this last equation that I showed here, we can expand the frequency, the quasi-normal frequency, to third order, like here, where we see some numbers here that are accompanying this potential. And it means that they are the derivative of this potential. For example, this V3 is the third derivative of the potential. And all this expression must be evaluated at the peak R0 of the potential. You also see this new number. New is the Overton number plus 1/2. And this expansion was made to third order, but it also works for fourth and sixth order at the equinal limit. Okay. So now we need to determine where is the peak of our potential. So this is easily determined by taking the first derivative of the potential and making it 0, and this will give us this R0. So to leading order in the equinal expansion, we see that we find this very simple equation. And something curious here is that this equation is very similar to the photon sphere equation. So if we write a function g given by this metric coefficient over r squared, we can rewrite this last equation in this form, okay? And we can also rewrite the photon sphere equation. And for this photon sphere equation, we have the inverse of this function here. And in this case, this is evaluated at the photon sphere radius. So now it comes to the crucial part of the work. We identify this R0, the maximum of our potential for the perturbation, with the photon sphere radius. And this can happen as long as 1/g² at the photon sphere radius is different from 0, what is always true in our case. So this is the main result of our work. If we have a spherically symmetric black hole which allows photon sphere orbits, and we introduce a field perturbation in this background, the maximum of the potential of the equation of motion of this perturbation corresponds to the point that signals the last circular null geodesic around the structure. So once we made this crucial identification, then we can match both sides of the correspondence. What we do here is to expand at equal limit this frequency that we had previously on this expression here. And for the imaginary part of the quasi-normal frequency, we have this result here. We see that this imaginary part is proportional to the inverse of the shadow radius. And for the real part, that is what we want to fix here, we found this very, very simple relation. And this relation has a contribution of the leading term and a first subleading term. This relation was conjectured by Yusufi in this paper published this year to the leading term. So now we proved this conjecture, and we also added this first order leading contribution. So now with this correspondence, we are going to show some examples in order to see if it is fulfilled by the class of spherically symmetric black holes that we are considering. So our first example is the d-dimensional Tangerlini black hole. In this case, the metric coefficient is given by this expression, and the angular part of the black hole can be written in this compact way. This parameter mu of the Tangerlini black hole is related to the physical mass of the black hole through this equation, where the volume of the angular part is given by this other equation here. Now, what we are going to do is to calculate first the things from the shadow side, and then the things from the quasi-normal frequency side. Okay, so from the shadow side, we will consider Lagrangian formalism in order to study null geodesics. So the Lagrangian is given here. And the radial equation that can be extracted from this Lagrangian for a photon geodesic is given by this other equation, where the potential in this Tangerlini black hole is given here. In this potential, we see some constants. This E is the constant of motion associated to the temporal part of the metric, so the energy of the particle, basically. And this L is the constant of motion associated to the second angular coordinate, the angular momentum of the particle. And this K is the constant that appears when we separate the angular part of the geodesic equation, and it is also known as the Carter constant. We are also considering that the first angular coordinate is fixed to pi/2, so the usual equatorial orbits. Now, we are going to find the photon sphere radius, and in order to do this, we have to apply the photon sphere conditions. So the conditions basically are that the potential must be 0 at this photon sphere radius. The first derivative is also 0, and the second derivative is negative at this point. So using these three conditions, we can find the photon sphere radius and a bonus relation between the energy and the angular momentum of the particle, these motion constants. So now that we have this photon sphere radius, we can calculate the shadow radius for our black hole. And this is given by this relation, the photon sphere radius over the square root of the metric coefficient evaluated at the same point. And we find this result. So we see that the shadow radius depends on the dimension and on the characteristics of our black hole. Okay, now from the quasi-normal frequencies side, we consider, for example, massive scalar perturbations in this background of the Tangerlini black hole. And we can separate the angular part as usual and put the rest of the equation in a Schrodinger-like form so that the potential of that equation is given by this expression here, where m is the mass of the scalar field that we are using as a perturbation. Again, it appears this multiple number associated to the angular momentum of the particle. And in order to find the frequencies that this potential produces, we will use a sixth-order WKB method. This sixth-order WKB method was developed by Canoplia as a generalization of the Eger and Will method that I showed previously. There is also another generalization of WKB until 12th order that was recently done by Matiasek and Opala. Now, in order to compare both sides of the conjecture, we will define some quantities here. This omega 0 is the first contribution to the conjecture, the leading contribution, and omega 1 is the leading in the first sub-leading contribution to the correspondence. So all results for the Tangerlini black hole are in this table. In this case, we are considering a 4-dimensional Tangerlini black hole. The first 4 lines here are the quasi-normal frequencies obtained through the WKB method. And the last 2 lines correspond to the frequencies obtained using the shadow radius. So what we can see here is that the correspondence works very well when we consider the first sub-leading term of our expression for the frequency. We also see that when we have grow the mass of our scalar field, also we have these frequencies growing. And we see that when we go to the econal limit, so L very large here, the correspondence is almost perfect and is independent of the mass of the perturbation. Now, we can also show some other table here for the 10-dimensional Tangerlini black hole. And in this case, we see similarly, the first 4 lines correspond to the quasi-normal frequencies using the WKB method. And the last 2 lines are the frequencies obtained through the shadow radius. And again, we see that considering the first sub-leading term, this correspondence is fulfilled in a very nice way. And something that we can also say, comparing these results in 10 dimensions and the previous results in 4 dimensions, is that the correspondence works better at lower dimensions. Now, our second example is a 4-dimensional black hole surrounded by an anisotropic fluid. This metric is written here, where m is the mass of the black hole, q is the charge of the black hole, c is a parameter related to the presence of this anisotropic fluid, and wf corresponds to the equation of state p equals wf rho, where p and rho are, as usual, the pressure and the density of this anisotropic fluid. This metric contains some special cases. For example, the Schwarzschild solution can be obtained if we make the charge and the anisotropic fluid parameter equals 0. Or if we make this charge 0 and WF equals 0, so that the mass of the Schwarzschild black hole is shifted to this value to m minus c. Another solution that is contained in this metric is the Schwarzschild ADS or Schwarzschild DS. And this happens when the charge is 0 and WF equals -1. And in this case, the cosmological constant is 3 times the anisotropic fluid parameter. Now, other solution that is also contained here is the Reisner-Nordstrom ADS or Reisner-Nordstrom DS solution. And this is when WF equals -1.
5 minutes, Berta.
Thank you, Damian. So we are going to do basically the same we did for the Tangalini black hole. We first calculate the things in the shadow side and then the things in the quasi-normal frequency side. So in the shadow side, as I detailed previously, we use some Lagrangian formalism. We find the radial equation of the null geodesic, and the potential in this case is given by this formula here, where this constant of motion L is related to the angular momentum of the particle. And applying the photon sphere conditions to this potential, we arrive to this equation that will give us a photon sphere radius. Now, for the quasi-normal frequency side, we're going to consider a scalar perturbation. And in this scalar perturbation, we again have a Schrödinger-like equation whose potential is given by this equation here. Okay. So now what we are going to do is to obtain the shadow radius, obtaining first this photon sphere radius, and then compare this shadow radius with that can be obtained from the quasi-normal frequency. All results are summarized in this table. So what we have here are the results for two cases, WF equals -1/2 and -2/3. In the first column, we have the shadow radius obtained from the real part of the quasi-normal frequency, again using the WKB approach. And we are considering the until the first subleading correction. And we see that these shadow radius here are almost the same as the shadow radius that we can find using the geodesic side. So this happens for both cases, for -1/2 and -2/3. And we can also see that with this subleading term, we obtain this perfect concordance between the two sides of the of this conjecture. Notice also that in this case, our result corresponds to the Econal limit when this multiple number is very high. And the Cmax that is appearing in our table is the value that avoids a naked singularity in this black hole. We also have some plot here. We plotted the shadow radius. This orange curve corresponds to the case WF equals -1/2, and the blue line corresponds to WF equals -2/3 for these mass and charge parameters. We see that as this anisotropic fluid parameter grows, the shadow radius also increases in this manner. Okay, so I just have 1 minute, one more minute. So let me conclude here. Let me summarize. Basically, the main result of our work is that we found an analytical relation between the Econal limit of the quasi-normal frequencies of a black hole and the shadow of the same black hole. And This was possible because in spherical symmetric black holes, we can identify the maximal location for the potentials corresponding to field perturbations and to null geodesics. And we illustrated this conjecture with two examples, one four-dimensional for black hole surrounded by an anisotropic fluid, and a d-dimensional black hole, that is the Tangerlini black hole, showing the validity of the correspondence. Thank you very much.
Thank you. Very nice for your talk, Berta. So let's take some questions. I think Alfredo is first.
So thank you, Berta, for this talk. I'd like to ask you, what is the physical motivation of considering this Tangerlini matrix as an example of a black hole? And then to ask you as well, why if you have the K, the Carter constant equal to different from zero, because you leave the K in your formula. And then you said as well that the theta was supposed to be equal to pi/2. As far as I understand, if you have, if you are in the equatorial plane, this K will be equal to zero, it will vanish.
Well, first of all, about the Tangerlini black hole. The motivation is to see if this conjecture can work for the dimensions and if there is some correction. And in fact, we found that there is some correction depending on that dimension. And of course, okay, the most realistic case nowadays is the four-dimensional, because we can see the black holes in all dimensionality. However, we don't know if in the future we can also see the projection of extra dimensions in, that can affect this shadow radius. Now about the Carter constant. The Carter constant does not enter in our conjecture. In fact, it just enters in this relation between the motion constants, okay? And that's why we call it a bonus relation, because it's not used in order to find the photon sphere radius. So whatever is this Carter constant, whatever value it has, we have the same result.
Yeah, but at that moment, did you fix the theta equals to pi/2?
Yes. I mean, this is the usual in the usual treatment in order to treat geodesics. It's just because of this. But
What I am saying is that as far as you fix this theta equals to pi/2, then the Carter constant should vanish.
Can you repeat your question, because it is, let me put my volume. Okay, can you repeat, please? This.
Do you fix the theta equals to pi/2? And if the Carter constant is still different from zero in your treatment?
Yes, it is possible. It is possible because the Carter constant is related to the d-4 angular coordinates. I mean, the first angular coordinate is what we fix. The second angular coordinates will give the angular momentum of the particle in that direction. And the other d-4 coordinates will be related to this Carter constant.
I see. Thank you.
So they are separated things.
Yes, thank you.
Well.
Eloy?
Hello, Berta.
Hello,
I am
Eloy.
confused with your result. Why do you call your result a correspondence, or you talk about the conjecture? How you emphasize very well at the all the properties that you can calculate from a black hole for example, the quasi-normal frequencies or the shadow of the radius shadows, all will depend on the parameters of the black hole. And all we know from returns that they are characterized by very few parameters. So it is obvious that any quantity that you will calculate there will be a sort of relation between these quantities.
Yes, sorry, Berta, we are hearing the echo from what Eloy is saying. Maybe you should mute your mic when you are not speaking or turn the volume down a little bit.
Okay.
Let's see if now, yeah.
Okay.
Much better, yeah.
Okay, my question is, I am a little confused with your result because for me it's a sort of obvious that if you calculate properties of the black holes will be relation between these because all will depend on the few parameters that characterize a black hole. So I don't really understand why you call this a correspondence. For me, it's a little obvious that you will be a functional relation between all the properties that you will calculate from a black hole.
Well, to us it was not obvious because you are taking different approaches. I mean, you are considering null geodesic. Okay, so you are considering photons that are orbiting a black hole, and from the other point of view, you are considering perturbations to a black hole that have nothing to do with this photon orbiting the black hole.
But
So
do you agree that
we are
all
matching
quantities,
these two things that apparently they don't have a relation, but what is more surprising to us is that even doing it numerically, it is a perfect relation.
but do you agree that all these properties will depend on the few parameters of the black hole? For example, in the case that you first analyzed.
Sure, but how can you? Yes, but how can you be sure that this correspondence can exist? I mean, you have to calculate.
What corresponds? In one case, you will have the shadow radius. It will depend on the mass, and the other case you will have the frequency. It will depend on the mass. It is obvious that there will be a relation between them. So why do you name this a correspondence?
But they are different approaches, I repeat. I mean, one is geodesics, and the other is perturbation. You are perturbing with any kind of perturbation, this black hole. I mean, this correspondence doesn't depend on the kind of perturbation. And this is something really surprising.
No, it's not surprising, sir.
Well, it's surprising to us. I'm sorry that it's not surprising to you.
What properties will depend on the mass?
No, but I mean, what is surprising is the relation, not that they depend.
Some relation. Who knows? There will be some relation because both depend on the mass.
Yeah, but why? For example, you can use the same argument to say, the imaginary part of the frequency should be related to another thing, and this is not so obvious.
Okay, thanks, Berta.
Okay.
Leo, last question.
All right. So my question is, so I think from the ADS-CFT point of view, this is quite interesting. I've been looking at some Lyapunov coefficient or exponent in some trajectories, and I mean, if what you're saying can be translated to ADS-CFT, that would be related to some thermodynamic properties of some field theory. So I wonder how much, or if you have looked at this question in asymptotically ADS spacetimes.
Well, in fact, it seems that it doesn't work in ADS spacetimes. It works for DS spacetimes, but not for ADS. And this is because in ADS, when you have some perturbation, the potential that you obtain from your perturbations doesn't go to a constant. So you cannot apply the WKB method, and so you cannot establish this correspondence. That's a problem.
Thank you so much.
Okay, we are amazingly on time, so let's do a 5 minutes break and resume with the last talk of the workshop at exactly the hour. Thanks, Berta, for the talk.
Thanks to you.
Alejandro, if you want to share your screen and check that everything works fine, this is your time.
Hi, can you hear me?
Yes, yes.
Okay, I will try the share screen then.
Great. Okay, perfect. Yeah, I can see it.
Yeah, okay, perfect.
All right, we start in 4 minutes or so.
Okay.
Okay, maybe we can start with the second talk of this session. The speaker will be Alejandro Vilar López from Universidad de Santiago de Compostela, and he will be telling us about entanglement entropy in qubit gravitational theories. Alejandro, all yours.
Okay, so thank you, and let me start by thanking the organizers for giving me the opportunity to talk here about entanglement entropy in qubit gravitational theories. This is work done in collaboration with Elena Cáceres and Rodrigo Castillo. It will be published soon, hopefully. And well, I would also like to start thanking them for their kind hospitality when I was in Texas, like last fall, where I started this work with them. So, as the title says, this will be a talk about entanglement entropy. You know, entanglement entropy is a very useful concept and allows us to gain significant physical insight into quantum field theories. Well, in particular, because it has to do with entanglement, which is probably one of the deepest concepts in quantum theory. The problem is that it is usually difficult to calculate. And luckily, in 2006, Ryu and Takayanagi proposed a way to calculate entanglement entropy in a holographic theory dual to general relativity. And in that case, it is possible to compute entanglement entropy as a geometric problem, basically finding the area of a minimal surface anchored to the boundary of the region we want to compute the entanglement entropy for. And since then, there has been a lot of work in this concept in the context of holography, and we have been realizing that this is probably a very deep statement and idea about quantum gravity. And well, there are many recent developments that show this, like entanglement wedge reconstruction, or well, even recent works in the information paradox have to do with entanglement in some sense. So as my title says as well, this will be a talk about cubic theories, so higher derivative gravity theories. And let me remind very briefly why they are important in the context of ADS-CFT. So first of all, they are expected as quantum or stringy corrections to the classical bulk action. So in a sense, they correspond to bulk corrections, which give you corrections to the strong coupling and large n limits of the conformal field theory. That is from a theoretical viewpoint, and from a more practical one, basically they allow you to access different holographic theories than the one you can access with general relativity. For example, just so theories that are non-supersymmetric or with different properties. So they are also useful as a toy model or as a way to explore different properties of field theories. So my goal here will be to show how entanglement entropy has to be calculated from the bulk viewpoint when you have a holographic theory dual to a general cubic gravity. So I will consider at the end a generic cubic gravity and show how this Ryu Takayanagi idea gets modified. So just to start with the more technical content, so let me remind how entanglement entropy in the field theory can be calculated. One of the ways to do it is a replica trick, and this will be useful to connect with the gravity results. So in the replica trick, basically you compute entanglement entropy for region A as a limit of range entropies. These range entropies are defined in this way. And the important thing is that you can compute these range entropies via a Euclidean path integral. So basically, you can show that these range entropies can be calculated with this partition function, Cn, which is the partition function of the theory in a Euclidean manifold, which is the n-fold cover. Basically, it's a manifold in which you have n copies of the original manifold, glued cyclically along the region you are considering to compute the entropy. So this is what I try to represent here with these circles. Basically, if you go around this, you change it. And so this is all field theory. But if your theory is dual to a gravitational one, basically this log of the partition function should be calculated using an on-shell Euclidean action of a dual solution, which is this Vn I put here. And then basically the entanglement entropy is just a derivative. You can manipulate this to obtain a derivative of this on-shell action. This was done by Lukovic and Matasen in 2013. And well, there's a small subtlety here which has to do with this hat I'm putting here. Basically, this hat means the following. So you see that in the boundary you have a CN symmetry because you have n copies of the same space, and you can change the order of these copies. In principle, you would expect this symmetry to be preserved in the bulk, and then you can quotient your dual solution Bn by this Cn symmetry, and basically you just at the end you get just one copy, so you get rid of the remaining ones, and then the action is n times the one you have in this single copy, which is after quotienting, which is the hat. That's the meaning of the hat, and this has some subtleties I will talk about in a minute, but. Basically, the important point up until here is that we have reduced the computation of entanglement entropy to a problem in classical gravity. You just have to compute this on-shell Euclidean action and take a derivative. So if you look at this, basically at n equals 1, you would expect that the bulk solution is a solution of the gravitational theory, because it's the dual solution to the original situation in the field theory. So in principle, this is a variation where you start from this solution and you are varying and taking a first order variation. This you would expect to be 0. And it is not because of this quotienting procedure I mentioned before. Basically, what happens is that for different ends, when you quotient, you get in the fixed points of the Cn symmetry, you get a conical singularity, basically. And the strength of that conical singularity is different for different ends. So when you are varying n, the boundary conditions at that conical singularity change. And that is what makes this different. This is not vanishing because of that, basically. And this also has another important consequence, which is that basically this right-hand side localizes in the conical singularity where you are changing boundary conditions. And in particular, when you take the n equals 1 limit after taking the derivative, basically the computation localizes in which would be the limit when you go to n, when you take n going to 1 of these conical singularities. Obviously, n in principle is a discrete variable; it's an integer, but you have to do an analytic continuation in the middle of this procedure, okay, to define this. Well, so if you do this, how this connects? This is what Lukovic and Mendocena show, and how this connects with the usual Ryuta-Kayanagi prescription. Well, basically, what you can show is if you do this procedure in general relativity, and you regularize the metric in this conical singularity, and you take this derivative, and you do all this, which is technically very complicated. Basically, you get that this expression is the area of the manifold, which is this limit of the conical singularities for different ends. Okay. So as I said, this is very difficult technically, but at the end you get that the entropy is the area of some manifold, which is this limit I write here. And then there's a second part, which is how do you determine the position of the surface for a generic bulk geometry. Well, what they do also in this paper is they consider this conical singularity, this regularized conical singularity. They study the equations of motion, and they look at which conditions one has to satisfy for this conical singularity to be a solution of the equations of motion. So what they get is that in general relativity, this surface has to satisfy this condition, which is that the trace of the extrinsic curvatures are 0. Basically, well, this surface is a codimension 2 manifold, so there are 2 extrinsic curvatures defined starting from the 2 normals, and this A is just an index leveling that. So, and this is the condition for a minimal area surface. So this is the point where you realize that basically what you have to do is you take this area functional, and then you minimize it, and then you get the Ryuta-Kayanagi prescription. So this is the connection with the usual Ryuta-Kayanagi prescription from a more abstract point of view, which will be useful now because we want to do this in higher derivative gravitational theories in which things are more complicated. But the idea is basically the same. So when you do all this derivative procedure and all that, you get a different form of the functional, which is more complicated. I will talk about this a little bit more in a minute, but basically this is the equivalent to the area thing in Ryuta-Kayanagi. You see, it's more complicated. It involves derivatives of the Lagrangian of your theory. And you have, well, just to clarify notation, you have 2 normal directions, which I label with an index A. Usually I use also adapted complex coordinates C and C bar, okay? So these are the normal directions. And then you have the tangent directions to that C1 manifold, which are the yi, okay? I will talk a little bit more about this functional in a minute. And then the second step is how I determine the surface. Well, in principle, you have to do all this difficult procedure of going to the equations of motion, and that is very difficult for a higher derivative theory. But there's a paper in 2017 by Dong and LAWGH in which they show that basically you can just minimize the result of this thing you do here, then you can minimize the functional and it works, just like it worked in general relativity, okay? So basically, once I have this functional, what is this? This is very strange. First of all, you have a sum in alpha, which I didn't explain, and I have to explain what I mean by this, okay? So this is the technically difficult part of this. Basically, before entering into details, what this is going to do for us, although it looks like a second derivative, this will generate higher order terms in the functional in extrinsic curvatures, okay? So just an example, if you have a cubic theory, then you take two derivatives of the Lagrangian, and this will give you a term which is Riemann kk. But this sum in alpha will also generate terms which are kk, kk. And if you go to fourth order, you would have Riemann square k square, but you would also have Riemann k to the fourth or k to the sixth. Basically, this is an implicit way of and a technically complicated way to generate higher order terms in this functional. Okay. So where does this sum in alpha and all this problem come from? Basically, the key step is the regularization of the conical singularity you have to do to take that n derivative I showed before. Basically, when you regularize, you have to be careful on how you regularize, because there are several ways to regularize a conical singularity in this manifold with the Cn symmetry. You can, for example, this is just a term of the full metric. You would get a term. You could get a term which is of this form. You have a CC bar here. Okay, but you could also put CC bar to the n, and you can show that this also is a valid regularization of the thing, and they give different contributions when you take the n derivative. Okay. So in principle, the way to decide is that you have to use the equations of motion of the theory. This was a problem which was called the splitting problem, and it was not well understood at first, and it has some technical difficulties. Okay, so all this boils down basically to this is a little bit technical. It's just to give an idea of how this works. The details are not very important, but the thing is that basically when you take this second derivative of the Lagrangian, then you have to expand your curvature tensor components in some other objects, which are the extrinsic curvatures, and some other things are tilde q, which are not very important. You expand that for every term, and then you have to count how many of these things have. Each of them counts as one. You have to count how many of these things you have, and each counts as 1/2. And then at the end, you divide by q alpha plus 1. And then you can undo this rewriting in terms of r tilde and q by going back to the usual curvature things and case. Basically, that's what you will get at the end. Okay. This I explained with this table here on the left. This was the original prescription given by Shidong in 2013, and I will call that the minimal prescription. Some years later, Joan Camps also proposed this other non-minimal prescription, which is a technically different. So you have to do some different substitutions, and at the end you get different terms in this higher order expansion in case. Okay, so this is a different prescription which would arise from a different regularization of the conical singularity. So as I said, in principle, none of these have to be valid for a general theory. Okay, you would have to regularize according to the equations of motion of your theory, which can be extremely complicated for a general higher order gravity. What we know is that at least this non-minimal prescription is perturbatively valid, because Joan Camps did this using the regularization imposed by the general relativity equations of motion. So basically, this term will be higher order. If you have a higher order theory, this will be proportional to the couplings of the higher order theory, because the GR Lagrangian has 0 second derivative. And then you can regularize to calculate everything here. You can regularize according to the GR equations of motion, because any change would be higher order. Okay, so this is valid perturbatively. That's the message. This one was the original proposal by Shidong. So an example that might be familiar for some of you, if you do this whole business with a generic quadratic Lagrangian, then you get a functional for the entanglement entropy, which has this form. Okay, this you see here kk terms and all that. This was already known because of the work of Fursaev, Patrushev, and Sholodukhin. Okay, this was known before this Dong and Camps business. You see that there's a single functional here. I didn't talk about splitting problem here for quadratic theories, and this is because the splitting problem does not affect quadratic LAWGH or f of r theories. Okay, in these cases, this splitting problem I just mentioned is irrelevant. Basically, it doesn't affect the form of your functional, but it does. It is important for cubic theories, and in fact, this is the first example in which you explicitly see this problem. So what we did was we consider a generic cubic gravitational theory. That means a combination of these 8 Lagrangians, okay, which are the 8 cubic gravitational densities, basically. And what we did was compute the functional for this generic Lagrangian. Well, I will not show the full thing here because it would be a mess, but what I will do is I will turn on just mu1 and show you the result for both the minimal and non-minimal prescription, and you see that you have terms RR, KKR, and K to the fourth, and there are some of them which are different because of these different prescriptions. Okay, so these are the functionals. So just to go to the final part. Okay, perfect. So just going to the final part of the talk, what we did also was to consider an explicit example of this in a case of a cubic theory, in a particular cubic theory. Okay, so we consider this cubic theory where P is this cubic density, which is called Einsteinian cubic gravity, was proposed by Pablo Bueno and Pablo Cano, and it's interesting because it has some nice properties, like that it has the same spectrum in NGR when linearized on a maximally symmetric background, and this is true for any dimension independently, so you don't have to change these coefficients in P. And interestingly, this theory is neither topological nor trivial in 4 dimensions, which is very interesting because it's the only cubic theory having the previous 2 properties which satisfy this, because you could consider, for example, cubic log, but that would be trivial in 4 dimensions. And well, this theory, they showed also that it is dual to a non-supersymmetric 3-dimensional CFT when you consider it in 4 dimensions. This theory also has another nice property, which is that it has good black holes. Good means that they are characterized by a single function, and this single function is it satisfies the second order differential equations, and you can obtain thermodynamic properties very nicely. And well, there's quite a lot of work on this. Okay, so we consider this theory, and we consider basically a boundary strip in 4-dimensional Poincare ADS. 4-dimensional Poincare ADS. This is the Poincare ADS. This is the radius of L star is the radius of curvature, which is related to the L in the Lagrangian by means of this F infinity, which has to satisfy this equation. This is due to the fact that you want your background to be a solution of Einsteinian cubic gravity, and we basically obtain the functional starting from the general formula I showed before. You can obtain the functional for this surface using symmetry as well, which is characterized in terms of this C of X function, and you get 2 different functionals for the minimal and non-minimal prescriptions. And just to try to see as an exploration, let's say, to see what are the difference of these functionals, we minimize them numerically, and we plotted the resulting surfaces in these plots here. Basically, the green thing is the Ryuta-Kayanagi surface for different values of mu. This is the surface you would obtain in GR, so for mu equals 0. And then in red you have the non-minimal, the one you obtain with the non-minimal prescription, and in blue the minimal one. We also plotted here the causal wedge because, well, since causal wedge inclusion should be respected, none of the surfaces should be below this one. And well, this was just a check. It's not very important here. But this, as I said, this was just an exploration to see how this thing with different prescriptions works. So let me go to the conclusions now. So basically what we did is that we obtained the entanglement entropy functional for a generic cubic gravitational theory using 2 prescriptions, which are the most common ones in the literature, just to see how this splitting problem arises here in an explicit example. And as an application of this, we show explicitly the difference for a strip in a 3-dimensional conformality theory, and we show the entanglement surfaces. So just to conclude, future work, part of it is also work in progress. I'm developing with Pablo Bueno. Hopefully it will be also in the archive soon. Well, the important thing here is that we have the correct perturbative functional for a generic cubic theory. So because of this, Joan-Camp's prescription is correct. So we can, if we stick to the perturbative regime, we can just evaluate it on the conventional RT surface. This is because the higher order terms, obviously, you can evaluate them on the unperturbed surface because they are already first order, and the leading order term, the area term, basically is minimal, so it's invariant under first order perturbations, and a first order perturbation of the surface doesn't change. Once you have this, what you can do is obtain leading order corrections to universal terms of entanglement entropy in symmetric regions, in general dimensions. For example, you could consider a ball in the CFT or some other shapes and compute the leading order corrections to the universal terms of entanglement entropy. This is interesting because some of these universal terms have an interpretation in terms of other quantities in the CFT, for example, central charges, and some others don't. So you get a lot of information of the CFT this way, okay? In particular, we obtain this way, for the first time, a corner function different from the GR1. The corner function is basically the universal term when you consider a corner in a three-dimensional field theory. And this is interesting because no corner function different from the year one was known up until now. And then just as a possible line of future work, you can try to do this in continue to higher orders in the curvature in your gravitational theory. Okay, so that's all. Thank you very much.
Thank you. Are there questions? Nicolás?
Let me unmute. Okay, so my question is there a specific combination of cubic coefficients such that the ambiguity does not appear?
Yes, for example, as I said, in LAWGH theory, in any dimension, you don't have this problem because basically, so in that case, you can see that this is a little bit technical, but when you do this alpha expansion and all that, basically the only components which are affected in curvature are those which have normal legs to the surface. And in LAWGH, everything becomes intrinsic, and you can see that, and that's why these Jacobson-Myers functionals and all that were known without all these problems, because basically for LAWGH this doesn't appear.
Okay, then I rephrase my question. Is there another combination other than LAWGH in which this does not happen?
Then I have to answer I don't know, but I would bet no.
Okay, thank you.
Because that's very particular of LAWGH.
Mm-hmm.
Carlos?
Alejandro, hola.
Hola.
Yeah, hola. So a couple of questions. One is a bit technical, the other just out of curiosity. So you have these two prescriptions, one by Camps, one by Sidong, right?
Mm-hmm.
Is it clear from the field theory what these two prescriptions are? What are you doing? Is it a different regularization? What is it? That's the first question.
Okay, so I would say no. I don't know exactly from the field theory viewpoint what is it, but if I have to answer, I would say that basically just one prescription. So entanglement entropy is defined clearly in terms of the field theory. You have this regularization problem and all that, but apart from that, the definition is one, and you should have one prescription in the body to compute it. So in principle, what you have to do is you have to go to the whole process, take the equations of motion, see which regularization you have to use. And when you do that, then you get the correct thing. The fact that there are several options is that this wasn't clear at first, and it's technically very difficult. So we wanted to explore until which point that was important. So are there differences in the prescription? And they are. So if one wants to do this correctly, then one has to do the whole process and decide which one is the correct functional. And in principle, it could be that neither the minimal nor the non-minimal one would be. In a general higher derivative theory, this is difficult.
If you calculate this entanglement entropy, say that you do it in a 4D CFT, right? So you have some ADS there, right? When you do the calculation explicitly. So one usually gets 1/L² that comes from the units and the coefficient, and all the interest is in the coefficient. If you go one prescription or the other, do you get a difference in that coefficient?
Yes.
And this is the comment you made me about the central charges or the.
Yes, that's the thing. In principle, it's conceivable that you can. So there are some cases in which these coefficients in entanglement entropy will have an interpretation in terms of other CFT quantities, and it would be interesting to see if that can discriminate between prescriptions and say one is wrong, the other is not. This is not. So this is an avenue to pursue, definitely.
The very last, and this out of curiosity, what happens if you have a Lagrangian that is not r plus r² plus r, etc., but if it is square root of r? Can you in some way go with this formalism?
I have no idea, actually. I would say
it's a bit tricky because you cannot expand it, right?
Yeah, that's the thing. What I was going to say is that if you can do a serious expansion, then I would bet that you can do the same. But otherwise, I would say I don't know. It's not clear that it's going to be valid for me.
Gracias. Very good.
Juan.
Hi. did you try spherical regions?
Yes, yeah, we looked at spherical regions. That's part of the work I'm doing with Pablo. I think he's in the audience, so
Did you? Okay, did you? Because I asked because you made this comparison with the causal wedge, and for spherical regions, at least in pure ADS, it coincides with RT, and you showed in 2 cases that I think one was above and one was below. So maybe even for spherical regions, you can say something more.
This I didn't do it in complete generality, non-perturbatively safe for a generic cubic theory, but I think this is going to happen. What is going to happen over spherical region is that the thing is so symmetric that nothing changes, because basically for a spherical region, your case, not the trace of the extrinsic curvature, but the extrinsic curvature is 0. So you see that the higher order terms in the functional are k to the second, k to the fourth, whatever, powers of k. So if you minimize that functional, that generic functional, then you will get some case plus variation of k, right? And if you have a surface which has 0k, then nothing will change when you minimize. So basically, I didn't explicitly do this in full generality for a general cubic theory, but my expectation would be that the region doesn't change.
Okay, and the other option is to consider black holes, because in that case, yeah, and at least for theories with 2 r squared, that's where this comparison with the causal wedge can make a difference, and you can it can lead to constraints on these couplings.
Yeah, that was actually just a small comment. That was actually one of our first motivations when we started looking at this, Elena, Rodrigo, and myself. But the problem with that is that in these theories, this fact that they only propagate the usual graviton only happens in maximally symmetric backgrounds. If you put a black hole, then in principle you will have new modes propagating, and some of them can be superluminal. And then you have all these difficulties then in which you have to deal to see which one is the fastest one, or stick to the causal wedge, or well, there's a whole discussion which gets more complicated there.
Yeah, but that's why it precisely that it might lead to non-trivial constraints.
Yeah, sure.
Okay, thank you.
Thank you.
Pedro?
Okay, hi. I think my question is the same as Juan, the first question by Juan, but maybe I will ask it again because I didn't got the answer correctly. In your drawings, you have this RT surface, and then the other surfaces you drawn, and then you have this entanglement wedge curve that was below. In every drawing I have seen, that maybe this is, I'm not very keen on the literature, but in all the drawings I have seen, this RT surface, and I am accustomed, or how do I say, I'm used to understand the entanglement wedge as everything that is in between this RT and the boundary. But in your problem, they don't match, right? Could you explain a little bit why?
So the question is why the causal wedge doesn't match with the RT surface, or because
yes, exactly that. Why is the reason? Is it because of higher derivative, or is it because of something else?
No. So the RT surface I plotted, the green one was the one you get in GR for this boundary strip. The thing is that they coincide when you have a spherical region. Maybe it's the typical situation in which you discuss this. I'm not very familiar with all the literature also, but that's my feeling. But if you consider these other regions, the thing that has to, because the causal wedge is defined basically shooting null rays into the bulk. So it's not an equivalent differentiation. It's the causal wedge is basically, if you want, the region to which the causal diamond of your boundary region can communicate, while the entanglement is defined by the RT surface. They are not the same thing. Okay.
Great. Thank you.
You're welcome.
Okay, I don't see any more raised hands, so let's thank the speaker first. Oh, there's one, Danilo. We have a minute for your question if you want to ask.
1 minute. Okay. Can you hear me?
Yeah, I can hear you.
Yeah. Can you hear me? Yes.
Yeah.
Question is, can you try one of the Riemann by box? I mean, by 2 derivatives. Can you do the computation, or there are some troubles there?
it gets more complicated. There's a paper by Miao, I think it's by Miao, in which basically he discusses all these, like what happens for a generic higher order gravity in which you can have explicit covariant derivatives. But things become way more complicated at the technical level. And since the conceptual things are already present here, we didn't go into that discussion.